What does it mean to say that space began, or that time itself had a birthday? It's one of those questions that sounds poetic until you realize physicists ask it quite seriously. If there truly was a beginning, then what does before even mean? Hello there, and welcome to the Sleepy Astronomer. I'm so glad you're here tonight. Wherever in the world you might be listening from, maybe beneath a clear night sky, or somewhere where the stars are hiding behind city light, I'd love to know where you're watching from. Feel free to share it in the comments. It's always wonderful seeing this little community stretching quietly across the planet. If you enjoy calm journeys through the cosmos, please consider giving the video a like and subscribing. It helps more than you'd imagine, and to those who've already subscribed, thank you sincerely. You're part of the reason these quiet explorations exist, and as always, I hope this video isn't too interesting. The goal, after all, is to help you drift off. But if you do happen to stay awake, at least you might learn something beautiful before you dream. So settle in, breathe slowly, and let's begin a gentle journey into one of the strangest ideas in all of cosmology: the notion of a time before space. Could it have existed at all? Time and space. They feel inseparable, yet our minds instinctively pull them apart. One is the stage, the other the rhythm of the play. But in the universe's deepest story, the two are threads of the same fabric, woven together so tightly that neither can exist without the other. When cosmologists talk about the beginning, they don't mean a sudden explosion in space. They mean that space itself was once compressed, dense, and hot beyond imagination, and then began to expand. It's not that stars burst outward from a point, but that the very distances between points began to stretch, carrying everything with them. The Big Bang, as it's often called, wasn't really a bang at all. It was the quietest possible miracle, the emergence of space, time, and energy from an initial condition that still defies full description. When we ask what came before, we start to press against the limits of our language, because time, as far as physics can tell, might have been born right alongside space itself. To understand this story, we'll have to rethink what we mean by both of those words. We'll explore how scientists measure time across billions of years, what it means to say the universe has an age, and why the notion of a before may not even make sense. We'll trace the clues written in starlight, the expansion of galaxies, the faint afterglow that fills the cosmos, and the delicate balance of the elements that formed long before the first star was born. But most importantly, we'll slow the pace. We'll wander through each idea as though through a quiet observatory at night, letting curiosity be our guide. By the end, the question may not be whether there was time before space, but how the two arose together in the same breath when the universe first opened its eyes. Time. It feels so obvious that we barely think to question it. We wake up, the sun rises, the day unfolds, and we assume that time is simply flowing onward, a steady river carrying us from past to future. But what exactly is this river made of? If you try to hold it in your hands, it slips through your fingers. Time, it seems, is both the most familiar thing in the universe and the most mysterious. For centuries, people have tried to define it. The ancient Greeks argued about whether time was real or just a convenient illusion. To Aristotle, time was a measure of change, the counting of motion, a way of tracking what happens and in what order. To him, if nothing ever changed, time itself would lose meaning. Centuries later, Sir Isaac Newton pictured time as a cosmic metronome, ticking evenly, independent of everything else, the same for all observers. In his view, Even if every star vanished, the invisible clock of the cosmos would keep on ticking in the dark. Then, in the early 20th century, Albert Einstein turned that idea inside out. He showed that time doesn't beat the same for everyone. It stretches and shrinks depending on how you move and where you are. Time is not separate from space. It's part of a single fabric that bends under the influence of gravity. A second on Earth is not quite the same as a second on the Moon. And at the edge of a black hole, time slows to a crawl, at least from the point of view of someone watching safely from afar. The ticking of the universe, it turns out, is not universal at all. But beyond the physics lies an even deeper question. Does time exist on its own, or is it born from change? Imagine a universe frozen in perfect stillness. No stars moving, no atoms vibrating, no light crossing space. Would time still pass there? What would it even mean to say that a minute had gone by if nothing had changed during it? Without change, time loses its heartbeat. Some physicists and philosophers believe this thought experiment points to a strange possibility, that time isn't a background stage where the universe performs, but a consequence of the performance itself. In daily life, we feel time through motion. We see it in the swing of a pendulum, the beat of a pulse, the orbit of the Earth. Ancient civilizations built sundials and water clocks to measure its flow, using the regular rhythm of nature as their reference. Later, mechanical clocks divided days into hours, minutes, and seconds, giving time the precision it never naturally had. And today, atomic clocks measure it using the tiny vibrations of cesium atoms, so regular they drift by less than a second in millions of years. Yet even these perfect clocks don't tell us what time is, they only tell us how to count it. At its core, time is a relationship, a way of describing the sequence of events. It's the difference between before and after, between then and now. Without events to order, there's nothing to measure. It might be more accurate to think of time as the universe's memory of change. Every process leaves behind traces, decaying particles, cooling stars, growing crystals. The arrow of time emerges because these traces always point one way, from less disorder to more. Things mix, decay, and spread out. A shattered cup doesn't reassemble. This is why you can remember the past but not the future. It's not that time forces things to move forward. It's that the universe naturally evolves from simple beginnings toward greater complexity. But there's another layer still. In the equations of physics, time is just another coordinate like height or width. Those equations don't care which way it flows. They work just as well backward as forward. If you filmed two billiard balls colliding and then played the video in reverse, you'd still see a plausible event. So why does time seem to have a direction at all? The answer may lie in the universe's starting conditions, a state of extraordinary order that set everything in motion. From that moment onward, entropy or disorder increased. Time's arrow was born not from the laws of nature themselves, but from the asymmetry of the beginning. We sense this arrow in everything we do. Our lives unfold like a one-way journey, memory behind us, mystery ahead. Yet, if you zoom out far enough, the universe may not share our sense of flow. From a cosmic perspective, past, present, and future could all coexist as different slices of one vast space-time structure, all equally real. What we call now might simply be the point our consciousness happens to be aware of. To us, time feels like motion. To the universe, it might be structure. Still, this raises a curious thought. If time depends on change, and change depends on the contents of the universe, matter, energy, light, then could there have been time before any of those existed? Could there have been earlier moments before the birth of matter itself? The problem is that every way we measure time depends on something physical ticking or moving. Without matter or energy, there are no clocks. Without clocks, the word before may have no meaning. Some physicists suggest that in the earlier stages of the cosmos, what we think of as time was not yet distinct from space. Instead, there was a more primitive kind of geometry, where distance and duration were blurred together. In such a picture, time crystallized out of chaos when the universe cooled and expanded enough to form stable laws. It's an unsettling idea that the flow of time could itself be a phase transition, the way water freezes into ice or steam condenses into liquid. Even language struggles to handle it. When we say before the Big Bang, we're already assuming the existence of time to mark a before. But if time emerged with the universe, that phrasing becomes meaningless, like asking what lies north of the North Pole. It's not that there's something there we can't see, it's that the concept itself stops making sense. So perhaps time isn't a river flowing around us, but a melody created by motion. When nothing changes, the music pauses. When things move, collide, and evolve, the song begins again. Our perception of its rhythm comes from being part of that grand orchestra of change. Every heartbeat, every orbit, every flicker of light contributing to the universal symphony. And yet, even knowing all this, time still feels personal. It stretches when we're waiting, it vanishes when we're happy, and it seems to accelerate as we grow older. No scientific definition captures that feeling. Time is as much an experience as it is a dimension. Perhaps that's its deepest secret. The universe measures time with expansion and decay, but we measure it with meaning. If everything in existence were suddenly frozen, every atom, every photon, every thought, time would vanish along with motion. But as long as something moves, changes, or grows, time will quietly unfold beside it. It may not exist on its own, but it exists with everything else. A companion to change, a rhythm of existence. And so the puzzle deepens. If the universe needed time to begin, yet time needed the universe to exist, how did the first second ever happen at all? Space. It sounds simple enough. The great silent backdrop against which everything happens. A vast emptiness, a cosmic stage. But that image, though comforting in its simplicity, is a little misleading. Because space is not just a place where things exist. Space itself is something. It has shape, it has structure, and it even has energy. Far from being a passive stage, space is one of the main actors in the grand performance of the universe. For most of human history, people imagined space as nothing more than a void, the absence of matter, the blank canvas between stars. To the ancient philosophers, it was a background so absolute that nothing could affect it. When Newton came along, he gave this void a sort of personality. Absolute space. It was fixed and eternal, an invisible grid on which all things moved. Objects could slide across it, but space itself never stirred. It was infinite, unchanging, and utterly indifferent to what happened within it. And for a while, that view worked beautifully. It let scientists chart planets, predict eclipses, and calculate trajectories with astonishing accuracy. But there were clues that this simple model wasn't quite enough. Light, for one thing, didn't behave as Newton's emptiness would suggest. It didn't need air or ether to travel. It crossed the void as though the void itself were doing the carrying. And then came Einstein. with a proposal that changed everything. Space isn't merely the setting, it's the script. According to Einstein's theory of general relativity, space and time are woven together into a single fabric, space-time, that can bend, stretch, and ripple. Matter tells this fabric how to curve, and the curvature tells matter how to move. The sun doesn't hold Earth in place with an invisible string of gravity. Instead, the sun warps the space-time around it, and Earth simply follows the curve, like a marble rolling along a gently sloped surface. Gravity isn't a force pulling down, it's the geometry of space pulling inward. To visualize this, imagine a heavy ball resting on a soft rubber sheet. The sheet dips under the weight, and any smaller ball placed nearby will naturally roll toward it. That's gravity in action, not as a mysterious attraction, but as motion through curved space. Now stretch that analogy into 3 dimensions, and add the element of time flowing through it, and you begin to glimpse the subtle beauty of space-time. It's not empty at all. It's an elastic field that flexes under pressure. But the surprises don't stop there. Space can expand. This was one of the most astonishing revelations of the 20th century. Astronomers discovered that distant galaxies are moving away from us, and not because they're speeding through space like shrapnel from an explosion, but because the space between galaxies is growing. Picture raisins in a rising loaf of bread. As the dough expands, the raisins move apart, even though they are not travelling through the dough itself. That's what our universe is doing on a cosmic scale. The dough is space, and it's swelling everywhere at once. This expansion isn't happening from a central point. There's no edge of the universe where the stretching begins. Every region of space expands in all directions, so wherever you stand, the galaxies seem to recede from you. It's an idea that sounds impossible until you realize that the expansion doesn't move objects through space. It changes what distance means. Over time, the very ruler we use to measure space gets longer. The scale of reality itself shifts quietly beneath our feet, and even when there's nothing in it, no stars, no planets, no light, space is never truly empty. Quantum physics tells us that the vacuum is alive with energy, a restless sea of flickering particles that pop into existence and vanish again faster than we can measure. In every cubic centimetre of so-called nothingness, countless virtual particles dance briefly into being, borrowing energy from the void itself before disappearing. What we call empty space is more like a simmering ocean at its most microscopic level. This hidden energy matters. It influences the behavior of the cosmos on the larger scales. Astronomers call it dark energy, a mysterious pressure that seems to be accelerating the expansion of the universe. We don't yet know exactly what it is, but it may be an intrinsic property of space itself. The energy of the vacuum. If so, then the universe isn't just filled with space, it is space, and space comes with its own vitality. When we look up at the night sky, we see distance. Between the stars lies darkness that seems infinite, but that darkness is not absence, it's substance. The geometry of space carries light, dictates motion, and shapes the destiny of galaxies. If you could somehow remove all the matter from the universe, the structure of space would still remain, though its shape might smooth out and its expansion would continue silently. Einstein's discovery transformed how we think about reality itself. Instead of space being the container for the universe, it became part of the universe's contents. When a star collapses into a black hole, it doesn't just vanish into nothing, it pulls the surrounding space inward, warping it so steeply that even light can't escape. The result isn't an object sitting in space, but a region of space behaving in a radically new way. Space is also dynamic on the tinier scales. Around massive objects it contracts slightly. Near the surface of Earth, space is a bit more compressed than it is in orbit. This is why clocks run fractionally slower down here. Time itself stretches and bends with the shape of space. You are at this very moment sitting in a gentle gravitational well sculpted by our planet, and that curve in space subtly changes the rhythm of everything you do, including your heartbeat. We tend to think of space as out there, as the vast expanse between stars. But space is right here too. It exists between atoms, inside molecules, and even between the protons and electrons within each atom. Most of what you consider solid matter is, in fact, mostly space, an intricate dance of fields held apart by forces. If you could scale an atom up to the size of a cathedral, its nucleus would be a grain of dust floating in the center, with electrons darting invisibly near the edges. Everything we touch is mostly void, structured and animated by the geometry of invisible fields. And yet, despite all its complexity, space remains the quietest thing imaginable. It carries no sound, no scent, no color of its own, only the echoes of what passes through it. It can be bent, stretched, and even torn, but it offers no resistance. It's both the gentlest and the most powerful feature of existence, the invisible skeleton on which the entire cosmos is built. Perhaps that's what makes it so easy to overlook. We live our whole lives inside space, yet rarely pause to think about it. It's not a nothingness to move through, but a something that moves with us. Every step, every thought, every breath unfolds within its invisible lattice. Space doesn't merely hold the universe together. It is the universe, in motion, in curvature, in constant expansion. And when we pair it with time, its inseparable twin, we find that what we thought was a stage is actually part of the story itself. Space doesn't just contain the play of the cosmos, it performs alongside it. There's a quiet elegance in realizing that space and time are not two separate things at all, but two sides of the same cosmic fabric. For most of history, people imagined them as distinct. Space was the container, infinite and silent. Time was the ticking clock that measured how things changed inside it. They seemed as different as night and day, one describing where, the other describing when. Yet in the early 1900s, a young patent clerk named Albert Einstein showed that they are deeply, inseparably connected. You can't truly understand one without the other. Einstein's insight was as simple as it was revolutionary. He proposed that space and time are woven together into a single, four-dimensional fabric called space-time. It's not that space exists first and time runs through it. Rather, they are stitched together, forming the very geometry of reality itself. Every star, every planet, every particle, and every one of us moves through this fabric along a path known as a world line. The shape of that path depends on how the fabric is stretched, and the fabric itself depends on what's in it. To imagine this, think of space-time as a soft, flexible grid, like a vast trampoline stretching in all directions. Place something massive on it, say a bowling ball, and the surface dips. Now, roll a marble nearby. The marble will spiral inward, not because the ball is pulling it with a force, but because the marble is following the curved lines of the surface. This is how gravity truly works. The sun doesn't pull Earth in a mysterious way across empty space. Instead, it bends the geometry of space-time around itself, and Earth simply moves along that curved geometry, following the straightest path it can. This picture is mind-bending because it turns gravity from a force into a form of geometry. And the geometry of space-time is not static. It evolves as matter and energy move around. Every planet, every beam of light, every breath you take slightly warps the space-time around it. Most of those distortions are unimaginably tiny, but they're there all the same. When something truly massive stirs, like two black holes colliding, the ripples in space-time can stretch across the cosmos traveling at the speed of light. We call them gravitational waves. They were only directly detected in 2015, a century after Einstein first predicted them, proving that space-time itself can tremble. But Einstein's theory did more than just redefine gravity. It redefined what it means to experience time. In this unified fabric, time doesn't flow at the same rate everywhere. The faster you move, or the deeper you are in a gravitational field, the slower time runs for you compared to someone else. This phenomenon, called time dilation, has been measured countless times. Clocks flown on airplanes tick ever so slightly slower than identical clocks left on the ground. Satellites orbiting Earth have to account for both gravitational and speed-related time dilation, so that GPS signals don't drift. Otherwise, your navigation system would quickly become useless. The effect may be small in our daily lives, but in the universe at large it becomes astonishing. Near a black hole, for instance, space-time is so distorted that time itself slows dramatically. To a distant observer, an object falling toward the event horizon seems to freeze, its clock ticking slower and slower until it stops entirely. From the falling object's point of view, though, it crosses the horizon normally and never notices the pause. The difference isn't an illusion, it's the geometry of space-time itself reshaping the meaning of time. Einstein's equations showed that time and space are measured differently depending on your motion, but always in a way that preserves the total structure of space-time. If you move quickly through space, you move slowly through time. If you move slowly through space, you drift more quickly through time. It's as if each of us has a constant speed through space-time, but we can trade between movement in space and passage through time. You experience this every moment. Even sitting still, you're moving forward through time at the fastest possible rate. This realization fundamentally changes how we think about the universe. Instead of a snapshot of things happening in sequence, space-time describes everything that has ever happened, or will happen, as part of a single, continuous geometry. Every event, from the birth of a star to a whispered conversation, exists as a point in this vast four-dimensional landscape. To us, it feels like we're moving through it, 1 second at a time, but from a broader perspective, the entire tapestry already exists. Past, present, and future are simply different regions of the same cosmic structure. That doesn't mean our experience of time is wrong. It means it's local. Each observer slices space-time in their own way, depending on how they move and where they are. Two people travelling at different speeds will disagree on what events are simultaneous. For one, 2 stars might seem to flicker at the same moment. For the other, one flash might precede the other. There's no universal now stretching across the cosmos. Every now belongs to someone. The universe doesn't tick like a single clock. It hums like an orchestra, each section playing its own rhythm, perfectly in tune with the geometry of space-time. Even light, that fastest of travellers, reveals the union of space and time. Because it moves at the ultimate speed, it experiences no passage of time at all. A photon emitted from a distant galaxy billions of years ago reaches your eyes tonight without aging a moment, gliding along space-time's surface as though all that distance and duration were compressed into one seamless journey. To light, space, and time collapse together into a single path. No intervals, no waiting, no before or after. Einstein once described gravity not as something acting in time, but as the shape of time itself. The Earth orbits the Sun because it's following the curve of time in that region of space. Every second that passes for us is the result of our world line bending gently through the four-dimensional fabric. If you could somehow step outside the universe and look at it from the outside, a thought experiment of course, you wouldn't see planets moving and stars shining in sequence. You'd see the entire history of the universe at once, like a sculpture rather than a film. Each moment would be a slice of space-time, layered one atop the next, forming a complete whole. The fusion of space and time also explains why you can't have one without the other. If you tried to remove time, all motion would stop, and space would lose meaning. There would be no way to define distance if nothing could change. Remove space, and time has nowhere to unfold. Every clock would freeze because there'd be no context for before and after. They're intertwined completely, not as partners who occasionally meet, but as a single being expressed in two ways. The deeper you think about it, the more beautiful it becomes. The universe doesn't exist in space and through time. It is space-time. It's not a stage and an actor. It's the entire performance, with its script, its rhythm, and its unfolding all at once. And while we move through it as travellers, from our small perspective, the cosmos itself simply is, a timeless structure where space and time, gravity and light, energy and matter are all woven into the same grand design. There's a quiet comfort in knowing that every moment we experience, every sunrise, every heartbeat, every instant of curiosity is part of that great fabric, seamlessly connected across the immensity of existence. In this sense, we're not merely in the universe. We are threads in its space-time tapestry, curving gently through the geometry of forever. If you could listen closely enough, the universe itself would seem to keep time, not with a tick or a chime, but with the quiet rhythm of expansion. Every moment since the beginning, space has been stretching, galaxies have been drifting, and light has been stretching with them. This cosmic rhythm, steady and patient, is the clock by which cosmologists tell the age of everything. It doesn't hang on a wall or sit on a wrist. It's written into the very fabric of space-time itself. We call it cosmic time, a universal measure of how long it has been since the universe began its expansion. While time for us depends on motion, gravity, and perspective, cosmic time offers something remarkable, a shared sense of now for the entire cosmos. Every galaxy, whether near or billions of light years away, shares roughly the same age of the universe. It's a clock that ticks not in seconds, but in the cooling of matter, the fading of light, and the unfolding of space. To imagine it, think of a great symphony orchestra scattered across a vast hall. Each musician sits at a different distance from the conductor, hearing the echoes at slightly different moments. Yet they all follow the same score, guided by the same rhythm. In a similar way, cosmic time provides the universal beat that unites galaxies across the observable universe. Even though they're separated by unimaginable distances, they share a common cosmic tempo. One that began when the universe first expanded from its hot, dense state nearly 14 billion years ago. It's strange to think of the universe having an age at all. After all, when you look out into space, you're also looking back in time. A galaxy 1 billion light years away appears not as it is now, but as it was 1 billion years ago. The farther we look, the younger the universe appears, until we reach the faint glow of the cosmic microwave background, the moment when light could finally travel freely through space. That light has been crossing the cosmos ever since, carrying with it a record of how long the journey has taken. So how do cosmologists tell what time it is for the universe? They don't wind up a clock, they read it in the data. The expansion of the universe, the stretching of a light from distant galaxies, acts like a natural chronometer. As space expands, light waves lengthen, shifting toward the red end of the spectrum. The greater the redshift, the farther back in time that light was emitted. By measuring this redshift and comparing it to the rate of expansion, scientists can calculate how much time has passed since the beginning. It's as if every photon in the sky was stamped with a tiny timestamp, telling us when and where it began its journey. Each one offers a clue about the tempo of cosmic time. Collect enough of them, and you can reconstruct the story of how fast the universe has been expanding, slowing down under the pull of gravity, and then speeding up again under the mysterious push of dark energy. Every change in that tempo is another tick of the cosmic clock. What makes cosmic time so remarkable is that it provides a consistent frame of reference for nearly everything large enough to be considered part of the cosmic flow. A galaxy drifting with the expansion of space is like a cork bobbing on a slowly widening ocean. The cork might move here and there with local currents, but on average it drifts with the swell. Likewise, galaxies may orbit, collide, or form clusters, but overall they move with the general expansion of the universe. For all such galaxies, the cosmic clock keeps roughly the same time. This shared time gives cosmologists a way to talk meaningfully about the universe's age. When scientists say the universe is around 13.8 billion years old, they're referring to cosmic time, the number of years since the expansion began, as measured by observers moving with the average flow of galaxies. Someone standing on a distant planet, watching the same sky from another corner of the cosmos, would reach essentially the same answer. That's what makes cosmic time so powerful. It's the one measure we can all theoretically agree on. Of course, now means something different depending on where you look. Because light takes time to travel, the universe doesn't have a single shared present in the everyday sense. You might be seeing a galaxy as it was 10 billion years ago, while that galaxy, if it could see you, would see Earth as it was 10 billion years in the past. Yet both of you still belong to the same cosmic timeline, each tracing its path through the same expanding space-time. It's like two travellers walking in opposite directions along the same road. They may be far apart, but they're still on the same map. As vast and impersonal as this cosmic clock sounds, there's something deeply human in the way it puts our lives into perspective. On Earth, we measure time in heartbeats and days, in birthdays and generations. Cosmic time measures in billions of years, in epochs and eons, yet we are part of that same flow. The calcium in our bones was forged in the cores of ancient stars whose clocks ran to the same cosmic rhythm. When they died and scattered their ashes across space, the universe's expansion carried those ashes into the clouds that eventually formed new suns and new worlds. Think of it this way. If cosmic time began when space itself began, then everything that has ever existed is part of one great unfolding moment. The first flicker of light, the birth of galaxies, the rise of life on Earth. All are milestones along the same timeline, written into the slow pulse of the universe's expansion. It's not so much a clock on the wall as it is a heartbeat, slow, deep, and impossibly long-lived. This heartbeat has changed over time. In the early universe, when everything was crowded and hot, expansion happened rapidly, like a newborn taking its first gasping breaths. Then gravity began to slow it, as matter tried to pull everything back together. For billions of years, the expansion decelerated, until dark energy, a mysterious form of energy embedded in space itself, began to dominate. Now the expansion is speeding up again, as if the universe were inhaling for the second time. Each phase, from rapid birth to slow adolescence to renewed acceleration, marks another tick of that universal clock. And yet, for all its immensity, cosmic time is intimately tied to us. The seconds that pass on your watch are tiny fractions of the same grand story. When you look at the night sky, you're seeing different pages of the universe's timeline spread out before you. Stars in their youth, galaxies in their prime, nebulae long gone. The cosmos displays its history all at once, while we experience it one moment at a time. It's humbling to realize that even as our own lives race by, the universe's clock barely stirs. Empires rise and fall, civilizations bloom and fade, yet on the cosmic scale, not even an instant passes. To the universe, 1,000,000 years is just a blink. Our entire species' history would fit in the tiniest fraction of one cosmic second. And still, we exist within that vast expanse, part of the same flow, bound to the same age-old rhythm. Cosmic time reminds us that we're not separate from the universe's story. We're among its most recent notes. The universe has been keeping time since the first instant, and every star, every atom, every heartbeat plays along. The cosmic clock ticks not to mark endings, but to measure expansion, transformation, and the quiet persistence of existence itself. So when you look up tonight, remember, the same clock that began nearly 14 billion years ago still keeps perfect time, quietly counting in the background as galaxies drift, as worlds turn, and as you breathe beneath the stars. For most of human history, the universe seemed eternal and unchanging, a grand stage that had always existed, with stars fixed in their patterns and galaxies assumed to be still. It was easy to believe that the cosmos simply was, timeless and infinite. But in the early 20th century, quiet observations through a telescope began to tell a different story, one in which the universe was not still at all, but stretching, growing, and evolving. It began, as great discoveries often do, with curiosity and good glass. In the 1920s, the astronomer Edwin Hubble used the newly built 100-inch telescope at Mount Wilson Observatory to study faint patches of light that had long puzzled astronomers. Were they clouds of gas within our own galaxy, or separate island universes far beyond? With the help of variable stars, celestial beacons whose brightness changes predictably, Hubble measured their distances and realized something astonishing. Those fuzzy smudges were entire galaxies, each containing billions of stars. The universe was far larger than anyone had imagined. But there was another surprise waiting. When Hubble and others examined the light from these galaxies through a prism, they found that its spectrum, the pattern of colours split like a cosmic barcode, was slightly shifted toward the red end. This shift wasn't random. The farther away the galaxy, the greater its redshift. It was as though the universe was singing in a deeper and deeper note the farther one listened. The explanation turned out to be revolutionary. When light waves stretch, their colour reddens. much like the sound of a passing siren drops in pitch as it moves away. This effect, called redshift, could mean one of two things. Either the galaxies were rushing away through space, or the space between us and them was expanding, stretching the light along the way. The second explanation fit the evidence perfectly. The galaxies weren't moving through space. Space itself was growing, carrying them with it. This insight didn't belong to Hubble alone. Years earlier, in 1927, a Belgian priest and physicist named Georges Lemaitre had proposed that the universe might be expanding, based on Einstein's own equations of general relativity. Lemaitre even suggested that if you rolled the clock backward, you'd find a time when all matter and energy were concentrated in a single, incredibly dense point, what he poetically called the primeval atom. At first, Einstein dismissed the idea as absurd. The universe, he thought, surely must be static. But the observations proved otherwise. Reality had outgrown the old models. Once scientists accepted that the universe was expanding, a natural question arose. If it's expanding now, was it smaller in the past? If galaxies are moving apart today, might they once have been close together? The answer was yes. The farther back you look, the more compressed and hotter everything becomes. Rewind far enough, and the entire universe was once packed into a tiny blazing state. A sea of energy and particles so dense that light itself could not escape. That idea became what we now call the Big Bang theory, though bang is a misleading word. It wasn't an explosion bursting into empty space, but an expansion of space itself, everywhere at once. There was no centre and no edge, just a smooth unfolding of the cosmos from an unimaginably hot beginning. But how do we know this picture is true? The first clue is that the expansion continues even now, as Hubble saw. The second comes from the faint afterglow of that fiery beginning, the cosmic microwave background. In the 1940s, physicists George Gamow, Ralph Alpha and Robert Herman predicted that if the universe had once been hot and dense, it should still be glowing with leftover radiation, cooled and stretched by billions of years of expansion. They even estimated its temperature, just a few degrees above absolute zero. But for decades, the prediction was forgotten, buried under other papers. Then, in 1964, two radio engineers at Bell Laboratories, Arno Penzias and Robert Wilson, stumbled upon a mysterious hiss while testing a new antenna. The signal came from every direction, day or night, and no matter how they adjusted the equipment, it wouldn't go away. At first, they suspected pigeons nesting in the antenna's horn. But when they cleaned it thoroughly, the hiss remained. Unbeknownst to them, a few miles away, a team of Princeton physicists was preparing to search for the very thing Penzias and Wilson had already found, the afterglow of creation itself. That faint background radiation turned out to be a perfect match for what the Big Bang model predicted. Today we call it the cosmic microwave background, or CMB for short. It's the oldest light we can see, released when the universe was about 380,000 years old, long before the first star ignited. Before that time, space was filled with a thick glowing plasma of electrons and protons. As the universe expanded and cooled, those particles combined to form neutral atoms, allowing light to travel freely for the first time. That light, stretched by the expansion of space, now bathes the entire cosmos as a soft microwave glow, only a few degrees above absolute zero. The CMB is astonishingly uniform, the same in every direction to 1 part in 100,000. Those tiny variations, tiny wrinkles in temperature and density, are the seeds from which galaxies eventually formed. It's like looking at the baby picture of the universe and seeing the faint freckles that would grow into stars, clusters, and cosmic webs billions of years later. Another piece of evidence comes from the chemistry of the cosmos. The abundance of the lightest elements, hydrogen, helium, and traces of lithium, tells a story consistent with a hot beginning. In the first few minutes after the universe began expanding, the temperatures were so high that atomic nuclei could form but atoms could not. Protons and neutrons fused briefly into helium and a dash of lithium before the universe cooled too much for fusion to continue. Those early elements forged in the first few minutes still make up most of the visible matter today. Stars later built the heavier elements, but the universe's initial recipe remains clear in every spectrum we observe. When you weave all of these clues together, the stretching of light from distant galaxies, the faint glow of the CMB, the chemical fingerprints of the early universe, the picture becomes impossible to ignore. The cosmos was once smaller, denser, and hotter, and it has been expanding and cooling ever since. Every observation points to that single extraordinary conclusion. The universe had a beginning, and yet that word, beginning, can be deceiving. It doesn't necessarily mean there was a before. Time itself may have been born alongside space, so that asking what happened earlier might be like asking what's north of the North Pole. The evidence shows us that the universe once existed in a state beyond anything we can truly imagine, but it doesn't yet tell us what, if anything, preceded it. Still, there's something deeply moving in the thought that we can see the echo of that first moment. Every photon of cosmic background radiation is a whisper, from the time when space first became transparent. Every atom of helium carries the memory of that early fusion, and every red-shifted galaxy drifting through the night sky reminds us that the universe is still expanding, still growing older, still unfolding the story that began nearly 14 billion years ago. From the faintest hiss on a radio receiver to the grandest sweep of galactic motion, every clue tells the same tale, that all we see, all we are, traces back to a single moment of transformation. The universe didn't simply begin in time. Time began with it, and that may be the most astonishing discovery of all. Imagine a universe without stars, without planets, without even atoms. Just a glowing fog of charged particles so dense that light couldn't travel more than a few centimeters before being scattered again. That was the early cosmos, a brilliant, featureless ocean of energy and matter. For hundreds of thousands of years after the Big Bang, light existed everywhere, but it couldn't go anywhere. The universe was bright, but blind. In those early times, space was unimaginably hot, tens of thousands of degrees, far hotter than the surface of the sun. At such temperatures, atoms couldn't exist. Every time an electron tried to bind to a proton to form hydrogen, the intense radiation around it immediately knocked it loose again. Photons, particles of light, were constantly colliding with free electrons, ricocheting in every direction like headlights in a dense fog. The universe, though filled with light, was completely opaque, but expansion changes everything. As space stretched, the energy of light was spread thinner, and the temperature of the universe began to fall. The once blinding fog cooled, little by little, until around 380,000 years after the Big Bang, a remarkable transformation occurred. The temperature dropped to roughly 3,000 degrees Celsius, still scorching by earthly standards, but cool enough for electrons to finally settle down and join with protons. Hydrogen atoms, stable and neutral, were born. This event is poetically known as recombination, though strictly speaking, it was the first combination of electrons and nuclei ever. With the electrons now bound, the universe's sea of charged particles disappeared, and suddenly light could move freely. The fog lifted. Photons that had been trapped for ages now streamed unimpeded through the newborn cosmos. Those first freely travelling photons are still with us today. Over nearly 14 billion years, the expansion of space has stretched their once blazing wavelengths into the microwave range, turning their fierce glow into a faint invisible hum. We detect them as the cosmic microwave background, the oldest light in the universe, a silent afterglow that fills the sky in every direction. It's astonishing to realize that this light has been traveling since long before the first star shone. When it began its journey, there were no galaxies, no planets, no eyes to see it. The universe was a vast uniform fog of hydrogen and helium, slowly cooling and beginning to form structure. Every photon of the cosmic microwave background carries a snapshot of that time, a frozen picture of the universe as it was in its infancy. If you could see microwaves with your eyes, the night sky wouldn't be black at all. It would glow faintly and evenly in every direction, a pale ancient light so uniform it's almost featureless. And yet, with these sensitive instruments, we can see that it's not perfectly smooth. There are tiny variations in temperature, differences of just a few millionths of a degree. These faint ripples are the imprints of slightly denser regions in the early universe, where gravity would later draw matter together to form galaxies and clusters. In those minute fluctuations lies the entire blueprint for the cosmic web we see today. When scientists first mapped the cosmic microwave background in detail, they were looking back almost to the beginning of time. Satellites like COBE, WMAP, and Planck have revealed the CMB in stunning precision, showing its delicate mottled pattern, the universe's baby picture. Each patch of slightly warmer or cooler radiation corresponds to a region where the density of matter was just a bit different. Over billions of years, those tiny differences grew, pulling in gas, igniting stars, and building the structures that fill the cosmos. It's hard not to feel a sense of intimacy in that image. The light that reaches us today has been travelling across space since before there were stars to illuminate it, before there was even dust to obscure it. It has crossed the entire history of the universe, drifting past the birth of galaxies, through the dark ages before the first stars, past supernovae and nebulae, and eventually down through the transparent air of Earth's atmosphere, where it is caught by our instruments and turned into data. That faint whisper of radiation connects us directly to the universe's childhood, and it's not just poetic, it's practical. The CMB allows scientists to measure the shape, size and age of the universe with extraordinary accuracy. The pattern of its ripples tells us that space is remarkably flat, that the universe is composed mostly of dark matter and dark energy, and that its expansion has followed a predictable rhythm. It is, in many ways, the most important piece of evidence we have about our origins, the light that never stopped travelling. What's perhaps most remarkable is that this light doesn't come from any single place. Because the universe was once so uniform, the glow comes equally from all directions. Every point in space sees itself at the centre of this cosmic afterglow, because the expansion happens everywhere at once. There is no privileged location, no cosmic spotlight. The universe is democratic in its brilliance. Every region contributes to the light that fills every other. If you are somehow able to stand in that early universe, Just as recombination was finishing, you would see a soft golden glow all around you. The light wouldn't come from stars but from the very air, a diffuse uniform radiance filling all of space. Over time, as expansion carried you forward, that glow would fade and redden until billions of years later it would become the invisible microwave background we see today. In a sense, we are living inside that ancient light, still bathed in the afterglow of creation. It's humbling to think that every photon of the cosmic microwave background has been travelling for nearly the entire history of the universe, unimpeded, unscattered, unchanged in its message. When our detectors catch one, it has completed a journey of almost 14 billion years without ever slowing down. It is the ultimate time traveller, a messenger from a universe that was simpler, smaller and hotter than we can easily imagine. And though it's ancient beyond comprehension, it's not silent. The CMB still hums faintly in the static of old television sets. Roughly 1% of the snow on an untuned screen is this cosmic signal, the same light that first broke free when atoms formed. Every time you see that flicker of static, you're glimpsing a whisper of the universe's first light. This moment, when the fog cleared and the cosmos became transparent, marks a profound turning point. It was the first time light could travel freely through space, the first time the universe could truly see itself. That light, stretched and cooled but never lost, still fills the sky, binding the past to the present in a single unbroken beam. When you gaze upward on a clear night, you see stars and galaxies, but beyond them lies that same primordial glow, the soft echo of the first dawn. It reminds us that we too are made of that same expanding universe, shaped by the ripples and rhythms of light that has been shining, unbroken, since the beginning of time. If you could somehow witness the first second of the universe, it wouldn't look like anything you recognize. There were no stars, no galaxies, not even atoms. The entire cosmos was a glowing ocean of particles, a seething, roiling plasma hotter than any furnace ever imagined. Space itself was still stretching at breathtaking speed, and time, newly born, was racing forward in its very first heartbeat. That single second would decide the basic ingredients of everything that would ever exist. In that instant, temperatures were beyond comprehension, trillions of degrees. Matter as we know it could not survive in such conditions. Instead of atoms or even nuclei, there was only a soup of quarks, gluons, electrons, neutrinos, and photons, all colliding in an energetic chaos. These were the fundamental building blocks of nature, dancing in a fiery equilibrium, constantly transforming from energy into matter and back again. The early universe was so dense that every particle was pressed shoulder to shoulder with countless others, exchanging energy in an endless cosmic shuffle. Photons smashed into electrons, quarks joined and broke apart, neutrinos streamed through like restless ghosts. Everything was so hot that even the strongest forces of nature behaved differently, merged together in a unity that no laboratory on Earth can replicate. But as the universe expanded, it began to cool, and with cooling came change. Around 1/10,000th of a second after the beginning, the temperature dropped enough for quarks to finally bind together, forming the first protons and neutrons. These tiny nuclei were the seeds of all the atoms that would one day exist, the first stable bits of matter in a cosmos that had previously been nothing but light and energy. This was a delicate balancing act. For every proton that formed, an antiproton appeared too, and when they met, they annihilated in a flash of pure energy. Somehow, For reasons we still don't fully understand, a tiny imbalance favoured matter ever so slightly, about one extra particle of matter for every billion pairs of matter and antimatter. That tiny excess, just a whisper in the chaos, is what survived to form stars, planets, and eventually us. Without that cosmic asymmetry, everything would have cancelled out, and the universe would be nothing but light. Within a few tenths of a second, another major event took place: the birth of the neutrinos. These elusive particles are among the most abundant in the universe, yet they barely interact with anything. Even now, trillions of them pass through your body every second, completely unnoticed. In the newborn universe, neutrinos were still in close contact with other particles, bouncing and colliding in the crowd. But as expansion carried everything apart, the density dropped, and the neutrinos slipped free, streaming out into the cosmos. From that moment onward, they barely interacted again. They became the first cosmic messengers, carrying a silent record of those earliest moments. A neutrino background that still fills the universe, even if we can barely detect it. Meanwhile, photons were also abundant and their energy dominated everything. The radiation pressure was so intense that it prevented matter from clumping together. Space was filled with light and fire, a kind of radiant storm where energy ruled and matter barely clung to existence. But with every microsecond that passed, expansion stretched space a little further and cooled it a little more. By the time the universe reached 1 full second of age, it had cooled to around 10 billion degrees, still unimaginably hot, but cool enough for many of the most violent reactions to end. Protons and neutrons now existed in a stable ratio, locked in a delicate balance determined by both chance and physics. That ratio would prove crucial in the minutes ahead, when these particles began fusing into the first atomic nuclei. Neutrons are unstable on their own. Left in isolation, they decay into protons within minutes. But in the early universe, reactions between protons, neutrons, and neutrinos kept converting one into the other. As the temperature dropped, those reactions slowed down and eventually froze out of equilibrium, fixing the number of protons and neutrons for good. Roughly 1 neutron remained for every 6 protons, a proportion that would later dictate how much helium formed when the first nuclear reactions began. The phrase "froze out" sounds almost peaceful, but it was anything but. It was the moment when the rapid-fire exchange of energy slowed enough that particles could no longer keep up with the expansion. Imagine a dance floor so crowded that everyone keeps bumping shoulders, and then suddenly the room doubles in size. The dancers drift apart and the music slows. The universe was doing the same thing, expanding so quickly that particles couldn't find each other as easily, locking in whatever balances existed at that instant. At about the same time, electrons, positrons, and photons continued their own furious exchanges. For every electron there was a partner positron, its mirror opposite. When they collided, they annihilated into pure light, flooding the universe with even more radiation. As with the protons and antiprotons, a tiny excess of electrons survived, just enough to eventually balance the positive charge of the protons. Without that coincidence, the universe would have been left electrically charged and unstable. It's remarkable to realize how much of the universe's future was decided in that 1 second. Every element, every star, every life form traces back to the outcomes of those early interactions. The balance between matter and antimatter, the number of neutrinos, the ratio of protons to neutrons, all of it set the stage for everything that followed. Had any of those numbers been even slightly different, the universe might have evolved into something entirely unrecognizable, or perhaps nothing at all. Though we can't see that first second directly, light couldn't travel freely yet. We can infer what happened through both theory and the clues left behind. The abundances of light elements, the structure of the cosmic microwave background, and the patterns of galaxies all carry faint echoes of those primal moments. In a way, cosmologists are like archaeologists, piecing together an ancient story from the fossils of energy and matter left scattered across the heavens. The sheer brevity of that first second is almost comical compared to what it achieved. In the time it takes to blink, the universe went from a field of pure energy to a sea of forming particles, set its fundamental ratios, and prepared the raw materials for every atom that would ever exist. It's hard not to marvel at how much happened so quickly, as though the cosmos was in a hurry to build a foundation before slowing down for the long, patient work of creation. As the universe crossed that 1 second mark, it entered a new era, cooler, calmer, and ready for the first nuclei to form. The wild storm of creation had settled into a rhythm. Neutrinos streamed silently into the dark. Matter began to outweigh radiation, and the cosmos for the first time started to resemble the universe we know today, still hot, still bright, but filled with the seeds of everything to come. In that single second, time and matter forged their first partnership. From that partnership would come the elements, the stars, the galaxies, and eventually us. Tiny creatures, billions of years later, tracing our ancestry back to the moment when the universe first found its balance between light and substance. The first second wasn't just the beginning of matter. It was the beginning of history itself, written in the language of physics and fire. Every story has a point where the trail fades, a boundary beyond which the map grows blank. For the universe, that frontier lies unimaginably close to its own beginning, in a region of time so brief that it defies ordinary language. Go back past the first second, past the first microsecond, past the first flicker of nuclear reactions, and you eventually arrive at a wall, the Planck wall. It marks the limit of what our current understanding can describe. Cross it, and physics itself starts to unravel. The number is breathtakingly small, about 1/10 trillion trillionth of a second after the universe began. That's a fraction so tiny that it makes even the blink of an eye seem eternal by comparison. It's called Planck time, named after the German physicist Max Planck, who first realized that nature might come with built-in units, smallest possible measures of length, time, and energy. At that scale, the universe was smaller than a single atom, yet it contained all the energy that would one day become galaxies, stars, and everything else. Physicists can trace the history of the cosmos with remarkable confidence back to that limit. They can describe the universe when it was a second old, a microsecond old, even a trillionth of a second old. But beyond Planck time, our equations break down completely. It's as if we've built a powerful telescope that can see nearly all the way back to the dawn, and then the lens fogs over, blinding us just as we approach the moment of creation. The reason is simple, yet profound. The two great pillars of modern physics, quantum mechanics and general relativity, are both exquisitely successful, but they speak different languages. Quantum mechanics governs the tiny world of atoms and particles, where randomness rules and probabilities dance. General relativity governs the vast scale of planets, stars and galaxies, where gravity shapes the grand curves of space-time. Each works perfectly in its own realm, but in the first instant of the universe, those two realms overlap completely. gravity becomes unimaginably strong and quantum effect become unavoidable. The result? A theoretical tug-of-war that neither theory can win. In the quantum world, energy fluctuates constantly, creating virtual particles that pop in and out of existence. In Einstein's world of relativity, energy curves space-time itself. Combine those ideas at extreme densities, and space-time would ripple and fluctuate violently, shredding the smooth geometry that relativity depends on. Instead of a continuous fabric, the universe may have looked like a frothing sea of bubbles, a quantum foam, where distance and duration themselves jitter and flicker unpredictably. It's an image that stretches the imagination. The Planck era, as it's called, lasted only that 1/10 trillion trillionth of a second, yet in that instant, all the laws of physics as we know them ceased to function in their familiar way. Space and time, the very scaffolding of reality, may not even have been distinct. Without clear geometry, the concepts of before and after, or near and far, lose their meaning. The universe wasn't just hot and dense. It may not have been spatial in any conventional sense at all. To many scientists, the Planck time represents not a beginning, but a horizon, the edge of what our current tools can reach. It's not necessarily the start of the universe, only the start of our understanding. Beyond it could lie anything: a smooth origin, a bounce from a previous universe, a quantum fluctuation in some deeper reality. The challenge is that no experiment on Earth can directly probe such conditions. The energies required are far beyond what even the most powerful particle accelerators can produce. For now, we are left to theorize, to build mathematical bridges over the fog. Various ideas attempt to do just that. String theory, for instance, proposes that the smallest building blocks of the universe aren't point-like particles but tiny vibrating strings. These strings would naturally include gravity and quantum mechanics in a single framework, smoothing out the wild fluctuations of space-time at the Planck scale. Other approaches, such as loop quantum gravity, imagine space-time itself as made of tiny discrete loops, like the threads in a woven fabric. At small enough scales, the continuous flow of space and time would break down into a network of quantized connections, giving the universe a kind of granular structure. No matter which idea turns out to be right, or whether the truth is something entirely unexpected, all of them agree on one thing: the smooth, classical picture of space-time can't survive all the way down. Our familiar laws are approximations, valid only above that mysterious threshold. Below it lies an entirely new kind of physics, waiting to be discovered. It's tempting to imagine that if we could just find the right theory, we'd finally know what really happened at the beginning, whether there was a singularity, a bounce, or some eternal quantum fluctuation that spawned our universe. But perhaps the real lesson of the Planck wall is humility. The universe is under no obligation to be simple enough for us to fully grasp. Every time we've peeled back a layer of mystery, another has appeared underneath. The Planck scale might simply be nature's way of reminding us that there will always be limits to what we can see and measure. And yet, those limits aren't discouraging. They're inspiring. Standing at the edge of knowledge has always been humanity's favourite place. The Planck wall doesn't close the door. It marks the doorway to a deeper level of understanding. It's where physics pauses, takes a breath, and admits, beyond this point the story continues, but we don't yet know the words. We can, however, make some educated guesses. If space-time was once a quantum foam, then the fluctuations within it could have seeded the very structure of the universe. Tiny wrinkles, magnified as the cosmos expanded, may have become the first variations in density, the same subtle irregularities we now see imprinted in the cosmic microwave background. In that sense, the universe's earliest chaos might have written the blueprint for all that followed, but the details remain tantalizingly out of reach. Our mathematics falters where gravity becomes quantum, and our instruments are blind to the smallest scales. Even light, our most reliable messenger, can't carry us back beyond the moment when space-time itself settled into its current form. It's as though the universe has drawn a soft curtain across its own first act, leaving us to reconstruct it from the echoes that remain. Still, there's a certain beauty in that mystery. Knowing that there's a place where our knowledge runs out gives science its sense of adventure. The Planck time may be unimaginably brief, but it's where the story of the universe, and of curiosity itself, truly begins. Every discovery we make, every new telescope or particle detector, is a way of pressing gently against that boundary, listening for the faintest whisper from the other side. Perhaps one day we'll have a theory that can bridge the gap between the quantum and the cosmic, one that lets us peer beyond the Planck wall and see the universe as it was, or as it first became. Until then, we stand at the edge of comprehension, gazing into a frontier where space, time, and imagination blur together. It's not failure to reach the limit. It's an invitation to keep climbing. And in that invitation lies something deeply human, a quiet acknowledgement that even at the edge of understanding, wonder remains. The Planck wall doesn't end the story of physics. It's simply the point where the universe, smiling enigmatically, says, "That's far enough for now." There was a moment in the universe's childhood so strange, so extreme, that it almost sounds like science fiction. In less than the blink of an eye, space itself is thought to have stretched from subatomic size to something vastly larger than a galaxy, a sudden, unbelievable burst of expansion known as cosmic inflation. It didn't just make the universe bigger, it reshaped its entire destiny. To understand why physicists propose such an astonishing idea, we need to rewind to the problems that troubled cosmology before inflation was conceived. The first was flatness. When scientists looked at the universe, they discovered that on large scales it seems perfectly balanced, not curved like a sphere or saddle, but almost exactly flat. That might not sound remarkable until you realize how precarious that balance is. For the universe to appear as flat as it does today, its density at the beginning had to be tuned to an absurd degree, within a fraction of a percent of the critical value. If it had been slightly greater, the universe would have collapsed long ago. Slightly less, and it would have flown apart too quickly for stars to form. It was as though the cosmos started life walking a cosmic tightrope with impossible precision. The second puzzle was uniformity. When we look across the sky, the cosmic microwave background, that faint afterglow of the early universe, is almost the same temperature in every direction. But according to the ordinary Big Bang model, regions of the sky that far apart could never have exchanged information. Light simply hadn't had enough time to travel between them before the universe expanded. So how did those far-flung areas know to match their temperatures so perfectly? It was as if two people on opposite sides of the world had somehow agreed to wear the same colour shirt without ever speaking. And then there was the monopole problem. Particle physics predicted that the early universe should have created exotic magnetic relics, magnetic monopoles, but not one has ever been found. Some mechanism must have diluted them to near non-existence. Enter inflation, the idea that space itself underwent an exponential growth spurt in the earliest sliver of time imaginable, somewhere around 1/100th of a trillionth of a trillionth of a trillionth of a second after the beginning. Proposed independently by Alan Guth and others in the early 1980s, the concept was breathtaking in its simplicity. If space expanded unimaginably fast for an unimaginably short moment, all three problems could be solved at once. Here's how it works. Imagine the universe as a tiny patch of quantum energy, curved and irregular, like a wrinkle in fabric. Then, due to a form of energy locked in space itself, what we call the inflaton field, that patch suddenly starts to stretch exponentially. Every tiny region doubles in size, then doubles again and again and again in rapid succession. In less than a heartbeat, something smaller than a proton becomes vastly larger than the entire observable universe today. Because everything expands together, any initial curvature would be stretched flat, just as the surface of a balloon looks flatter as it grows. This explains why the universe appears so precisely balanced. Inflation ironed out its wrinkles. It also explains why the cosmos looks uniform. Before inflation, the entire universe we can now see was once a tiny connected region, small enough for heat and light to even out its temperature. Inflation then magnified that region to cosmic size, freezing in its uniformity. And as a bonus, all those unwanted monopoles were diluted to near extinction, scattered across an expanse too vast to ever notice them. The result is the smooth, even universe we observe today, calm, cool, and almost perfectly homogeneous. But within that calm lies the key to everything. Tiny imperfections, faint ripples born from quantum fluctuations during inflation. Even in the vacuum of space, quantum uncertainty never rests. Tiny fluctuations in energy constantly appear and vanish, like ripples on a pond too small to see. During inflation, those minuscule quantum jitters were suddenly stretched to macroscopic scales. Places with slightly more energy expanded a little faster, while places with slightly less lagged behind. When inflation ended and the universe settled into a more ordinary expansion, those subtle variations became permanent. They were the seeds of structure, the first imprints of what would become galaxies, stars, and planets. It's extraordinary to think that the reason galaxies exist at all may come down to quantum noise in the first instant of creation. The tiniest possible uncertainties, magnified by unimaginable expansion, became the scaffolding for everything. The night sky itself, all its shining stars and swirling nebulae, might owe its existence to the restless flicker of a vacuum. When inflation finally ended, the universe didn't just stop expanding, it reheated violently. The energy stored in the inflating field poured into particles and radiation, filling space with the hot plasma that would later cool into atoms. This transition set the stage for the familiar Big Bang expansion that continued afterward, slower, steadier, but now vast enough and smooth enough to evolve into the universe we inhabit. For all its power, inflation isn't yet confirmed beyond doubt. It's supported indirectly by the smoothness of the cosmic microwave background and the flatness of the cosmos, but scientists are still searching for more direct evidence, especially the faint fingerprints inflation would leave in the polarization of that ancient light, or in the pattern of primordial gravitational waves. These ripples in space-time, if ever detected, would be the smoking gun, the echo of the universe's fastest moment of growth. What makes inflation so elegant is how it transforms a chaotic birth into an orderly cosmos. It takes the edge of mystery and smooths it into something coherent, yet it also raises new questions. What caused inflation to start? What made it stop? Could it happen again? Some versions of the theory even suggest that inflation never truly ended everywhere, that it might continue eternally in distant regions, spawning countless bubble universes, each with its own laws of physics. In that grander picture, our universe could be just one bubble in a cosmic sea, a serene oasis amid endless inflation. But even if that's true, it doesn't make our universe any less remarkable. It simply means that our cosmic patch was one of the lucky ones where inflation ended, where energy cooled, and where matter could gather into stars and life could wonder about it all. It's humbling to think that all of this, from galaxies to goldfish, might trace back to an instant so brief it defies imagination, when space itself stretched faster than light. That's not a violation of physics. Light's speed limits motion through space, not the stretching of space itself. Inflation didn't move objects faster than light. It moved the very fabric beneath them. It's a subtle but essential difference, one that turns the impossible into the beautifully plausible. If you tried to compress the story of inflation into a metaphor, you might say the universe sneezed, a tiny, almost imperceptible twitch that changed everything. Or, as one physicist once joked, the universe went through a period of rapid weight gain. In far less than a trillionth of a second, it grew from quantum scale to cosmic scale. That's the fastest growth spurt in history, and thankfully the only one that didn't require a new wardrobe. When inflation ended, the universe had expanded by an unimaginable factor, possibly more than a trillion times its original size. Yet the beauty lies not in the numbers but in what followed. The birth of order from chaos, of structure from randomness. Inflation turned a wild quantum flicker into a universe vast, calm and astonishingly uniform, ready to host stars, galaxies and everything that would one day look up and ask how it all began. Imagine the universe right after inflation, vast beyond comprehension, yet eerily empty. Space had just expanded faster than light could cross it, stretching every ripple of energy into near nothingness. The violent growth spurt that smoothed the cosmos also left it cold, silent and dark. For a moment it seemed the show was over before it had properly begun. But deep within that immense emptiness, energy was about to transform again, and in doing so, it would ignite the universe's first true dawn. This rebirth is known as reheating, the moment when the cosmos lit its furnace for the very first time. Inflation, as extraordinary as it was, had a curious side effect. It left behind a universe dominated by the energy of the field that drove it, the inflaton field. During the rapid expansion, this field stored energy like a tightly wound spring. When inflation ended, that energy had to go somewhere. It couldn't simply vanish. And so, as the field decayed, it released its stored energy explosively, filling space with a flood of radiation and particles. The universe went from nearly empty to unimaginably full, a sea of heat and light roaring into being. To picture it, imagine a kettle that's been quietly building pressure, its lid trembling but not yet whistling. Inflation was the tension, reheating was the whistle, the sudden release of energy that changed everything. For the first time, the universe was not just space expanding, but a place alive with matter. Every proton, electron, neutrino and photon that exists today traces its ancestry to that moment when the inflaton field gave up its energy to fuel the cosmic fire. In the instant before reheating, the temperature of space had plummeted to near absolute zero, colder than any vacuum we could ever produce in a lab. But as soon as the inflaton decayed, that frigid calm was obliterated. Temperatures skyrocketed to perhaps a quadrillion degrees or more. That's a one followed by 15 zeros, hot enough to break apart anything into its most fundamental constituents. Quarks and gluons, the raw ingredients of protons and neutrons, swirled freely in a dense incandescent soup. This was the universe's true beginning as a physical place. The light released in that first instant didn't illuminate stars. There were no stars yet, but it filled every corner of space, transforming the vacuum into a cosmic plasma. Particles collided, annihilated, and reformed in a storm of energy exchanges. Photons scattered in every direction, unable to travel far before striking another particle. Gravity, the weakest but most patient of the forces, began to take note, pulling slightly denser regions together in preparation for the structures that would come much later. It's tempting to call reheating the universe's Big Bang in spirit, even though technically inflation came first. What people once imagined as a single explosive beginning was, in truth, this transformation, the conversion of energy into matter, the moment when the universe became hot and radiant. The bang wasn't an explosion into space, but the birth of heat within space itself. The physics of reheating remains one of the great frontiers of cosmology. We don't yet know exactly how the inflaton field decayed, only that it must have done so. Some models imagine it oscillating wildly, dumping its energy into other particles in bursts, like a cosmic engine sputtering to life. Others suggest it decayed more gently, releasing energy continuously as the universe expanded. Whatever the details, the result was the same. A universe transformed from cold potential to blazing actuality. Within moments, the newborn cosmos was teeming with particles of every kind. Quarks and antiquarks, leptons and antileptons, photons, neutrinos, and exotic particles that existed only briefly before disappearing. Matter and antimatter annihilated in spectacular flashes, producing even more light. Yet somehow, as with every earlier epoch, a tiny imbalance remained, a whisper of extra matter left over after the mutual destruction. That whisper was enough. It would go on to form everything that exists. As the fiery chaos continued, the universe began to settle into a rhythm. Expansion cooled the plasma just enough for the strong nuclear force to confine quarks into protons and neutrons, sturdy building blocks that would soon join to create the first atomic nuclei. The early universe, once featureless, now had texture, a faint hint of structure in the swirling energy field. The term reheating might sound like a simple warming up, but it was far more dramatic than that. It was the conversion of the universe's stored potential into real, tangible energy and mass. It was nature's first great act of recycling, pure energy becoming the raw material of existence. The light produced then was the ancestor of every photon that will ever shine. The particle created then were the grandparents of every atom in every star and every breath you've ever taken. It's easy to think of reheating as just another step in a long sequence, but it carries a kind of poetic significance. Before this, space existed, but it was empty, sterile and silent. Afterward, it was filled with motion, radiation, and potential. It was, in a sense, when the universe first woke up. Even though we can't see directly into the reheating era, the light from that moment has long since been stretched beyond any wavelength we can detect. We can trace its fingerprints. The energy released set the initial conditions for everything that followed. The cosmic microwave background, the balance of matter and radiation, the density fluctuations that grew into galaxies. The universe we see today is the cooled, expanded descendant of that first furnace. Every time you look at the night sky, you're seeing the long-cooled embers of that first fire. In the cosmic timeline, reheating was astonishingly brief. Within fractions of a second, the universe had gone from cold vacuum to searing plasma, from near nothing to everything. But in that flash of time, all the basic ingredients of reality were forged. Not the elements themselves, but the energy and particles from which all elements would later come. And just as quickly as it ignited, the universe began to cool again. Expansion, the relentless metronome of the cosmos, continued its steady beat, diluting the heat and energy of the young universe. What had been a blazing storm settled into a more stable, predictable flow. The particles thinned out, collisions became rarer, and the radiation began to dominate. The next chapters of cosmic history, the formation of nuclei, atoms, stars, were all waiting in the wings. But the stage itself had finally been set. The beauty of reheating lies in its dual nature, both cataclysmic and creative. It was violent, chaotic, and spectacularly energetic, yet it was also gentle in its outcome, leaving behind a universe exquisitely balanced and primed for life billions of years later. It took what was once pure energy and turned it into the possibility of form, structure, and meaning. You could say that reheating was the moment the universe took a deep breath after its sprint through inflation, and exhaled everything we now see. It was the switch that turned the lights on in the cosmic workshop, the spark that started every subsequent process. The stars that burn in distant galaxies, the heat in your morning coffee, the photons that warm your skin on a sunny day, all are echoes of that first great ignition. And if the universe had a sense of humour, perhaps it would smile at the idea that it once experienced the mother of all warm-ups. In the briefest fraction of a second, it went from frozen emptiness to blazing brilliance. The fastest, hottest, most productive reheat cycle in history. After that, everything else, galaxies, planets, and people, was simply a matter of cooling down. As the universe cooled from its blistering beginnings, it went through a series of changes that would shape everything to come, not unlike what happens when steam condenses into water or when molten metal hardens into a solid. Physicists call these events phase transitions, and though they occurred on a cosmic scale, the underlying idea is surprisingly familiar. Just as a cooling cup of tea forms ripples as it settles, the cooling universe began to organize itself, separating its once blended forces into distinct parts. In its earliest moments, the universe was too hot for individuality. The fundamental forces we now know, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, were fused into one grand unified interaction. At such extreme temperatures, nature's laws were symmetrical and simple, but as space expanded and temperatures fell, that symmetry could no longer hold. The forces began to diverge, each taking on its own character and range. This breaking of unity is what physicists poetically call symmetry breaking. To imagine what that means, think of a perfectly smooth ball balanced on the very tip of a hill. The situation is symmetric. The ball could roll in any direction, and all directions look the same, but the moment the ball tips and begins to roll, that symmetry is lost. a single direction is chosen and the world changes as a result. In the early universe, symmetry breaking worked much the same way. As conditions cooled, fields that had once been perfectly balanced chose particular states, shattering the uniformity and creating new physical laws in the process. The first of these cosmic transitions probably happened almost immediately after inflation ended, when the universe cooled enough for the strong nuclear force to split away from the others. The strong force binds quarks into protons and neutrons, giving matter its structure. Later, as the universe cooled further, the weak nuclear force and electromagnetism, once indistinguishable, also went their separate ways. That event, the electroweak phase transition, defined how particles would interact for the rest of time. Symmetry breaking may sound abstract, but it is one of the most important concepts in physics. Without it, the universe would have remained a featureless soup, devoid of the complexity that allows atoms, chemistry, and life to exist. When the cosmic symmetries broke, they didn't break evenly. Some regions chose one configuration while others chose another, much like ice crystals forming with different orientations in a freezing pond. The boundaries between these regions could, in theory, leave behind imperfections in the structure of space itself, features known as cosmic defects. These defects are thought to come in several varieties: domain walls, cosmic strings, monopoles, and textures. You can imagine them as the faint scars left behind when the universe solidified. A cosmic string, for instance, would be like a hairline crack formed when the fabric of space cooled too quickly. These features, if they exist, might thread through the cosmos invisibly, carrying vast amounts of energy in an infinitesimally thin line. But despite decades of searching, no convincing evidence of them has yet been found. Their absence, in fact, helped inspire theories like inflation, which could have stretched any such imperfections far beyond our observable universe. The analogy between cosmic and everyday phase transitions goes even further. When water freezes, the molecules line up in a repeating crystal pattern, releasing latent heat in the process. Similarly, when the universe underwent its own transitions, energy was released and redistributed. The cooling wasn't uniform. Tiny fluctuations in density and temperature emerged, creating the seeds of future structure. These fluctuations were minuscule, but over billions of years, gravity would amplify them into galaxies and clusters of galaxies. The universe's smooth beginnings, paradoxically, depended on its ability to wrinkle ever so slightly during these cosmic freezings. In each phase transition, the universe lost some of its earlier symmetry but gained new possibilities. What had once been a uniform, featureless energy field became a world with distinct forces and stable particles. The strong force locked quarks inside protons and neutrons. The electromagnetic force bound electrons to nuclei, forming atoms. The weak force guided radioactive decay and fusion inside stars. These differences gave rise to chemistry, to light, and to the long chain of cause and effect that led eventually to life. It's worth pausing to appreciate how counterintuitive this is. We tend to think of symmetry as beauty, order, and perfection, something to be desired. Yet, in the universe, it was the breaking of symmetry that made beauty possible. Perfect symmetry, as it turns out, is sterile. Only when it fractured did the universe begin to express variety, structure, and change. It was as though nature had been holding its breath, and when it finally exhaled, reality diversified into everything we know. The cooling universe wasn't a calm process. Each transition released tremendous energy, sometimes in bursts that rippled through space-time itself. These ripples, gravitational waves born from ancient symmetry breaking, may still echo faintly across the cosmos, though detecting them is a formidable challenge. They would be unimaginably faint, whispers from an era when the universe was less than a trillionth of a second old. If we could hear them, they would tell us how space itself first took shape. Some physicists suspect that each major phase transition left subtle fingerprints that we might one day observe, not only in gravitational waves, but in the distribution of galaxies or the polarization patterns of the cosmic microwave background. Every bit of structure we see today, from the clustering of stars to the chemical elements inside your body, ultimately traces back to these early cosmic reorganizations. Even though these events took place in fractions of a second, they set the rules that still govern reality. The laws of physics aren't arbitrary. They are the outcome of how the universe cooled and crystallized in its youth. You could say that physics itself is fossilized history, the memory of those ancient cosmic transitions encoded into the very behavior of matter and energy. It's remarkable how something as vast as the universe can behave like something as ordinary as freezing water or solidifying metal. The same mathematics that describes how iron cools into a magnet can, in broad strokes, describe how space-time cooled into its current form. This shared logic reminds us that the universe is continuous. From the smallest atom to the grandest galaxy, everything follows the same underlying rhythm of change. And perhaps the most poetic part of all is that the universe's journey from unity to diversity is still unfolding. Even now, as space continues to expand and cool, we are witnessing new forms of structure, galaxies forming, stars dying, elements combining, planets coalescing. Every phase transition, large or small, is a reminder that change is written into the fabric of existence. In those early moments, as cosmic symmetries shattered and the forces of nature took their separate paths, the universe was writing its own rules, laws that would remain constant for billions of years. Those invisible decisions made in the furnace of creation now shape the fall of every apple, the warmth of every sunrise, and the chemistry of every living cell. The cosmos, in cooling, became creative. Its symmetry broke, and from that imperfection, everything beautiful was born. In the earliest moments of the universe, creation was fair to a fault. Every particle that came into existence was accompanied by its perfect opposite, a mirror twin of equal mass and opposite charge. For every electron there was a positron, for every proton an antiproton. Matter and antimatter were born as cosmic dance partners, swirling together in perfect balance. And if that symmetry had remained exact, it would have spelled disaster for everything we know, because when matter and antimatter meet, they annihilate, disappearing in a flash of pure energy. Had the universe stayed perfectly even, all of existence would have ended in light. No atoms, no stars, no planets, no us. Just radiation filling an empty, eternal void. And yet, here we are. Proof that the balance was broken. Somehow, in those first fractions of a second, the universe favoured matter ever so slightly. For every billion pairs of matter and antimatter particles, there was just one extra matter particle left over. That tiny difference, 1 in a billion, became everything. All the galaxies, all the stars, every mountain and molecule, every heartbeat and thought. This great mystery is known as baryogenesis, from the Greek words for heavy and origin. It refers to the process that created more baryons, the family of particles that includes protons and neutrons, than their antimatter counterparts. Physicists have spent decades trying to understand how this imbalance happened. The laws of nature, as we know them, treat matter and antimatter almost identically. Yet, almost is the key word. Somewhere, in the chaos of the newborn cosmos, a tiny flaw crept in, a subtle bias written into the universe's own rulebook. To grasp the scale of this imbalance, imagine flipping a coin 1 billion times and getting heads one more time than tails. That single extra head decides everything. The energy of the universe, all those particles and antiparticles, mostly annihilated into light, leaving behind a faint residue of matter that would one day condense into the galaxies we see. It's one of the most delicate coincidences in existence. Too much asymmetry, and the universe would have been choked with matter. Too little, and it would have vanished entirely in a sea of radiation. Instead, it landed on perfection. Just enough matter to make stars, but not enough to slow the cosmos into collapse. But how did nature tip the scales? The answer lies in the subtle quirks of the fundamental forces, particularly in how some interactions break what's called charge parity symmetry, or CP symmetry for short. In essence, this means that the laws of physics are not perfectly symmetrical when you swap matter for antimatter and look in a mirror. Most processes behave identically in both directions, but certain reactions, especially those involving the weak nuclear force, show a minute preference for one over the other. That tiny bias, multiplied across countless reactions in the early universe, may have been enough to give matter the upper hand. Experiments on Earth have confirmed that this kind of symmetry breaking exists, though it's incredibly subtle. Physicists have observed it in the decays of particles like kaons and B mesons, strange, short-lived creatures that flicker in and out of existence inside particle accelerators. These decays show that nature does indeed treat matter and antimatter slightly differently. The question is whether that difference is large enough to explain the vast cosmic imbalance we see. So far, the answer is uncertain. Our universe might be hinting at deeper principles we haven't yet uncovered, hidden mechanisms that favoured matter in the primordial inferno. Some theories suggest that baryogenesis might have occurred during one of the universe's early phase transitions, when the fundamental forces separated from one another. In such turbulent conditions, fields could have behaved asymmetrically, creating pockets of excess matter before the universe cooled and stabilized. Other ideas involve exotic particles, hypothetical heavy bosons or right-handed neutrinos that might have decayed in ways that slightly favored matter. None of these possibilities have yet been proven, but all point toward one profound idea. The universe, even in its most fundamental nature, might contain a built-in preference for existence. What's astonishing is how precarious that preference was. In the cosmic ledger, the universe's profit, the matter that survived, was 1/1000th of its budget. The rest annihilated in spectacular flashes, releasing an immense flood of photons. Those photons still exist today, cooled and stretched into the faint microwaves of the cosmic background radiation. In a poetic way, that radiation is the afterglow of annihilation, the echo of everything that didn't make it. And yet that small remainder was enough to build everything. Each atom in your body is a survivor, descended from that 1 in a billion imbalance. The carbon in your DNA, the calcium in your bones, the iron in your blood. All of it owes its existence to the fact that matter won a microscopic victory over its twin. Every breath you take is an act of cosmic favoritism. It's humbling to realize how easily it could have gone the other way. Had the universe been perfectly fair, we wouldn't be here to admire its fairness. It's one of those delicious ironies of existence. Only an imperfect universe can produce observers who notice the imperfection. Fairness, it turns out, is sterile. A touch of imbalance. That's where creation begins. Scientists continue to chase the mystery of baryogenesis because it sits at the intersection of our most successful theories and their greatest limitations. The Standard Model of particle physics describes how matter behaves with extraordinary precision, yet it doesn't provide enough asymmetry to explain our existence. Something beyond that model, a deeper layer of reality, must be responsible. Every new particle accelerator, every neutrino experiment is a step toward uncovering the mechanism that tipped the balance in favor of matter. Meanwhile, the consequences of that imbalance are visible everywhere. The stars that shine are made from the leftover matter. The galaxies that swirl across space are the residue of a cosmic near annihilation. Even the faint glow between galaxies, the cosmic microwave background, is a monument to the energy released when matter and antimatter destroyed each other. The universe we see today is quite literally what was left behind after almost everything else was erased. And perhaps that's the most poetic truth of all. We are made of survivors, of particles that escaped annihilation by the slimmest of odds. Every atom in every living thing is a record of that ancient triumph. The light from distant galaxies, the elements forged in stars, even the warmth of sunlight on your skin, all of it traces back to that one tiny, improbable imbalance in the earliest universe. So the next time you look up at the night sky, remember that the stars themselves are evidence of a cosmic unfairness, one that worked out in our favor. The universe, in its first moments, broke its perfect symmetry just enough to let something, rather than nothing, endure. And from that almost invisible victory of matter over antimatter, the story of everything began. The universe began as almost perfect, a smooth sea of energy and matter, the same in every direction to 1 part in 100,000. It was a balance so precise that it's hard to imagine anything interesting ever emerging from it. Yet within that calm uniformity were faint ripples, tiny variations in density, the whisper of unevenness left behind by inflation. Those minute differences would become the seeds of everything large, the subtle wrinkles from which galaxies, stars, and eventually life would form. The story of how those ripples grew is, in a sense, the story of structure itself, how time leaves its handwriting upon space. In the beginning, gravity was weak, almost patient. The universe was still filled with hot plasma, where light and matter were tightly bound together, scattering endlessly in all directions. Any attempt by gravity to pull matter into clumps was resisted by the pressure of radiation. It was like trying to build sandcastles out of waves. The moment a clump began to form, the sea of photons would wash it away. Only when the universe cooled enough for neutral atoms to form, hundreds of thousands of years later, could gravity finally get to work. Once light could travel freely, the universe became transparent, and matter was left on its own. The tiny overdense regions, those that had just a fraction more matter than their surroundings, began to grow. Gravity is a feedback loop. The more matter a region has, the stronger its pull becomes, attracting even more material. Slowly, over millions of years, the slightly denser regions drew in gas and dark matter, while the emptier regions grew emptier still. The universe was beginning to take on texture, a delicate cosmic lacework of filaments and voids. The real architects of this structure were not the atoms we're made of, but something far more elusive: dark matter. Though invisible to light, it makes up most of the universe's matter, roughly 5 times more than all ordinary matter combined. Unlike normal matter, dark matter doesn't interact with light or heat. It doesn't collide, radiate, or clump in quite the same way. But it does feel gravity, and that was enough to shape the cosmos. Imagine the early universe as a vast fog of hydrogen and helium floating through a skeleton made of dark matter. Those invisible filaments acted like scaffolding, guiding where ordinary matter could gather. In regions where dark matter was denser, gravity pulled in gas, forming the first clouds that would one day ignite as stars. Between these filaments lay enormous voids, empty expanses spanning hundreds of millions of light years, the silent spaces between the great cosmic web. This interplay between dark matter and ordinary matter defined the architecture of the universe. The dark matter condensed first, forming immense halos, gravitational wells that ordinary gas could fall into. As that gas collapsed under its own weight, it heated, swirled, and eventually ignited. The first stars were born. They were nothing like the gentle yellow suns we know today. These were giants, massive, short-lived, and brilliant beyond imagination. Their light pierced the surrounding darkness, reionizing the hydrogen fog that had filled space since recombination. The age of darkness ended, and the universe lit up once more. Those first stars changed everything. When they lived, they burned hydrogen into heavier elements. When they died, they exploded, scattering those elements across space. Each supernova enriched its surroundings with carbon, oxygen, and iron, the raw ingredients for planets and life. New generations of stars formed from that enriched gas, smaller and longer lived, gathering into the first galaxies. From those faint ripples in the early plasma came vast systems of hundreds of billions of stars, swirling in elegant spirals and glowing clusters. Meanwhile, gravity continued its slow artistry. Small galaxies merged into larger ones, drawn together along the filaments of dark matter like beads sliding along invisible strings. Clusters formed, then superclusters, and finally the great web-like pattern that astronomers observe today. Seen on the larger scales, the universe resembles a 3-dimensional lace, dense knots connected by filaments with immense voids between them. It's one of nature's most beautiful patterns, and it all began with fluctuations far smaller than an atom. The balance between dark matter and ordinary matter shaped this grand design in subtle ways. Because dark matter doesn't radiate away energy, it could clump much earlier, forming deep gravitational wells long before ordinary matter cooled enough to join in. That head start allowed structure to grow quickly once the universe became transparent. Without dark matter's invisible support, gravity alone would never have had enough time to form the galaxies we see. The universe would still be a smooth fog, with no stars, no planets, and no observers to notice its perfection. Even today, dark matter continues to hold galaxies together. If you measure the speed of stars orbiting within a galaxy, you find they move far faster than visible matter alone could explain. Without the extra gravitational pull of dark matter, the stars at the edges should have flown off into space long ago. Whatever dark matter is, a new kind of particle, a hidden field, or something even stranger, it remains the quiet glue of the cosmos, unseen but essential. The growth of structure in the universe is a story told across billions of years, written in the slow language of gravity. Early on, density variations grew linearly, like gentle ripples on a pond. Later, as matter accumulated, they became non-linear, collapsing into filaments and halos, fragmenting into clouds, stars, and galaxies. Each new structure built upon the last, creating a hierarchy that continues even now. Within galaxies, stars form and cluster. Within stars, atoms fuse. Within atoms, nuclei hold tight against the forces that would tear them apart. The same pattern, of smaller within larger, runs from the quantum scale to the cosmic web. It's worth pausing to realize how long this took. The first galaxies appeared a few 100 million years after the Big Bang, a blink compared to the universe's total age, yet still unimaginably long on human scales. The Milky Way, our home, began assembling perhaps 13 billion years ago. Its oldest stars still shine faintly in the halo that surrounds it, silent witnesses to a time when the cosmos was young. From a few parts per 100,000 in density contrast, gravity sculpted everything we see, a process both inevitable and miraculous. The universe didn't need a grand design. It needed only time and the laws of physics. From simplicity, complexity arose naturally, guided by attraction and balance. Today, when astronomers map the cosmos using surveys that chart millions of galaxies, they see that same faint pattern repeated on every scale. The ripples imprinted in the cosmic microwave background have grown into the scaffolding of the modern universe. The peaks and valleys of ancient density fluctuations are now the locations of galaxy clusters and cosmic voids. Time has turned quantum noise into the architecture of existence. There's a quiet poetry in that. The idea that the vast grandeur of the night sky was born from the tiniest imperfections. If the early universe had been perfectly uniform, gravity would have had nothing to work with. The fact that it wasn't, that it had just the right amount of unevenness, is why anything exists at all. It's a reminder that imperfection is not a flaw, but a creative force. The cosmic web continues to evolve, though slowly now. Galaxies still merge, stars still form and die. The handwriting of time continues to trace new shapes across the canvas of space. Each cluster, each nebula, each glowing spiral is a letter in that script. A record of how gravity, light, and matter compose the universe's long, unfolding story. When you gaze at the stars, you're looking at that story in progress. Every point of light is a punctuation mark in a sentence that began nearly 14 billion years ago, when tiny ripples in the early plasma began to grow. Those ripples became galaxies. Those galaxies became homes for stars. And from those stars came the elements that made you, a living fragment of that same ancient pattern written in starlight and time. Time, for all its familiarity, hides one of the deepest mysteries in science. Why does it flow only one way? Every moment carries us from past to future, never in reverse. Ice melts, but never unmelts. Stars age, but never grow young again. You can remember yesterday, but never tomorrow. This steady, irreversible drift is so fundamental to our experience that it feels obvious, and yet, when you look closely at the laws of physics, there's nothing in them that demands it. The equations work just as well backward as forward. So what gives time its direction? The answer lies in a single quiet principle that governs everything from galaxies to teacups: entropy. Entropy is the measure of disorder, or more precisely, the number of ways a system can be arranged without changing its overall appearance. A neat stack of papers has low entropy because there's only one way to keep them perfectly aligned. A messy pile has high entropy because there are countless ways for the papers to be scattered and still look the same kind of messy. The second law of thermodynamics tells us that in a closed system, like the universe, entropy tends to increase. Order gives way to disorder, not because anything forces it to, but because disorder is simply more likely. Imagine a hot cup of tea on a cool morning. The tea cools because energy naturally spreads out. Heat flows from the warm liquid into the surrounding air until everything reaches the same temperature. You never see it happen in reverse. The air doesn't spontaneously focus its energy back into the tea to reheat it. That would mean a local decrease in entropy, an incredibly unlikely arrangement of atoms conspiring to undo their natural spread. Time, in this everyday example, flows in the direction that entropy increases. This simple observation, that entropy rises, is the foundation of the arrow of time. It explains why we experience a before and after, why the universe evolves, and why life itself can exist. But here's the twist. For entropy to increase, it must start low. And the early universe, right after the Big Bang, was astonishingly low in entropy. That may sound strange. After all, the early cosmos was incredibly hot and dense, filled with particles colliding at unimaginable energies. Wouldn't that make it high in disorder? In one sense, yes. On the microscopic scale, it was a chaotic plasma. But entropy isn't just about heat. It's about how energy and matter are arranged in space. And gravitationally speaking, the early universe was remarkably uniform. Every direction looked the same. Every region had almost the same density. Paradoxically, that smoothness represents an extremely low entropy state, because there are far fewer ways for matter to be evenly spread than clumped together. Gravity, given time, prefers to make structure, stars, galaxies, black holes, all of which have much higher entropy. In that sense, the universe began like a neatly arranged deck of cards, ordered, balanced, and ready to be shuffled. Every process since then, from the formation of galaxies to the cooling of stars, has been part of that great shuffling. Entropy has been increasing ever since, and time's arrow has been pointing forward along with it. This cosmic asymmetry, the low entropy beginning, is what allows everything else to happen. Without it, there would be no gradients, no differences to drive change. Stars shine because heat flows from hot interiors to cooler space. Life thrives because energy flows from the sun to the earth and then radiates back into space. Every motion, every process, every act of creation depends on that flow from order to disorder. If the universe had begun in perfect equilibrium, there would have been nothing to evolve, nothing to remember, and nothing to feel the passage of time. Entropy gives us the direction of time, but it also gives us meaning. It explains why we see eggs break but never unbreak, why smoke disperses but never reassembles, why your memories belong to the past rather than the future. When you recall an event, you're accessing a record, a trace left by a physical process that increased entropy. The arrow of time is woven into the fabric of memory itself. Still, it's fascinating to realize that, in principle, the fundamental laws of physics don't care which way time runs. If you filmed two billiard balls colliding on a frictionless table, then reversed the footage, you'd have no way to tell which direction was forward. The interactions are perfectly reversible. The arrow of time emerges only when you add complexity, when countless particles interact, and the probability of returning to order becomes effectively zero. The arrow isn't drawn by individual particles, but by statistics. Time's flow is the most probable story the universe can tell. Everyday life is full of small reminders of this grand principle. Ice cubes melt into water, but water doesn't refreeze itself in a warm room. A building takes months to construct, but seconds to collapse. The stars we see shining now are slowly converting hydrogen into helium, releasing light in the process, an irreversible flow of energy from concentrated to diffuse. Even your body is an engine of entropy, taking in ordered molecules and releasing heat and waste, maintaining a fleeting pocket of order by exporting disorder to your surroundings. Life, in that sense, is a beautiful defiance of entropy, but only temporarily. We borrow low-entropy energy to build and grow, paying it back by increasing the universe's total entropy in the end. The same principle applies on cosmic scales. Stars burn, galaxies form and collide, and black holes swallow matter. All steps in the universe's progression toward higher entropy. Black holes, in fact, are the champions of disorder. Each one carries an enormous amount of entropy, proportional to the surface area of its event horizon. When a star collapses into a black hole, its entropy skyrockets, marking one of the most dramatic increases in the cosmos. Eventually, as the universe continues to expand and cool, these processes will slow and entropy will approach its maximum. In that distant future, no new structures will form, no stars will shine. Only a cold, dilute sea of particles will remain. Physicists call this imagined end the heat death of the universe. Not fiery destruction, but perfect silent equilibrium. Time, in any meaningful sense, would lose its direction entirely. Yet in the meantime, that rising entropy is what gives us the richness of the cosmos. The same tendency that drives ice to melt also drives galaxies to swirl, stars to ignite, and chemical reactions to unfold. It's the reason there are sunsets, music, and motion. The arrow of time, born from the universe's improbable beginning, is the quiet rhythm behind everything we experience. There's a gentle irony in all of this. The very process that ensures change and creation also guarantees decay. Entropy increases, and so stars burn out, mountains erode, and memories fade. But without that increase, nothing would happen at all. Time's flow is both our fate and our gift, the reason we can live, think, and wonder before fading back into the same equilibrium that birthed us. When you hold a melting ice cube or watch tea grow cold, you're witnessing the same law that governs the evolution of galaxies. Each act of cooling, each sigh of dispersal, is a tiny echo of the universe's journey from order to chaos. The arrow of time isn't just an abstract rule of physics, it's the story of transformation, written everywhere from the smallest cell to the grandest cluster of galaxies. And so time flows forward, always increasing entropy, always expanding possibility, carrying us, gently and irreversibly, from the simplicity of the beginning toward the intricate, beautiful complexity of now. It's one of the oldest questions anyone has ever asked. What came before the beginning? It feels like the kind of question that should have an answer, because everything we know has a before. Every sunrise follows a night. Every birthday follows the year before it. And even the universe itself feels like it ought to have had something that came first, a kind of cosmic prologue. But when scientists peer back through the equations that describe the cosmos, they reach a peculiar conclusion. The question, what happened before the universe began, might not make sense at all. The problem starts with the way we use the word before. It assumes that time is something that always existed, stretching infinitely backward like an endless road. But time, according to modern physics, isn't a background that events simply occur in. It's part of the universe itself, woven together with space into the fabric of space-time. And if space-time itself began with the universe, then asking what happened before that moment is like asking what's north of the North Pole. The question sounds meaningful, but it points outside the realm where the concept applies. This idea is unsettling at first because it challenges our most basic intuitions. We experience time as a constant companion, always ticking, always flowing. But in the earliest moments of the universe, time may have been so tangled with quantum uncertainty that its familiar flow simply didn't exist yet. In that primordial state, there was no earlier or later, just a timeless sea of potential waiting to unfold. Einstein's theory of relativity showed that time is elastic. It bends, stretches, and slows depending on gravity and motion. Near a black hole, for instance, time dilates so dramatically that an hour for one observer might be centuries for another far away. If gravity can distort time like that, imagine what happens when the entire universe is compressed into an infinitesimal point. Under such conditions, the very notion of time may lose meaning. There's no clock ticking in the singularity of the Big Bang because there's no stable framework for measuring change. Some physicists have suggested that instead of the universe emerging in time, time itself might have emerged with the universe, a property that crystallized as space expanded and cooled. In that view, asking what came before the Big Bang is like asking what happened before time itself began to tick. It's not that there's a forbidden realm we can't see, it's that the question no longer fits the territory. Yet science being science, the imagination refuses to stop there. There are models that try to describe what the universe might have looked like if you could somehow peel back that first instant. One of them is the quantum cosmology picture, where the early universe is treated as a kind of quantum wave, not a definite thing, but a cloud of possibilities. In this view, time as we know it doesn't exist at the deepest level. Instead, it emerges when the universe becomes large and classical enough for change to have meaning. The passage of time could be an illusion born from correlations between quantum states, a kind of cosmic rhythm appearing from an underlying timeless harmony. Another idea is the no-boundary proposal, developed by Stephen Hawking and James Hartle. It suggests that the universe may not have a beginning in the ordinary sense at all. Instead, time near the Big Bang might have behaved like another dimension of space. Just as Earth has no edge or boundary when you travel north, only the smooth curve of the globe, the universe may have no boundary in time. The Big Bang wouldn't be a hard starting point, but a transition, where the concept of time simply stops being applicable. Beyond that north pole of time, the word before ceases to mean anything. There are even more speculative ideas. Some propose that the universe may have experienced a bounce, that before expanding it was contracting, collapsing from a previous cosmic cycle. In that case, our Big Bang wouldn't be the absolute beginning, but a rebirth, one in an infinite series of expansions and contractions. Others imagine a multiverse, where our universe is just one bubble among countless others, each with its own space-time and its own beginning. But even these models don't always imply a before in the traditional sense, because time itself may be local, different in each bubble, rather than universal. The deeper you look, the more the line between physics and philosophy begins to blur. When we talk about beginnings, we're really talking about cause and effect, and causality itself only makes sense within time. To ask what caused time is a bit like asking what lights up the sun. Time doesn't happen inside the universe. It is the framework that makes happening possible. If the universe has a beginning, then the cause of that beginning would have to exist outside of time, and outside of time, cause and effect stop having their ordinary meanings. Still, it's perfectly natural to wonder. Humans are storytelling creatures, and every story we know begins somewhere. It feels wrong to think of a story that just is, without a first page. But physics invites us to consider that maybe the universe doesn't need one. The Big Bang may not have been the opening scene of a play, but the moment when the stage, the lights, and even the idea of sequence came into being. Asking what happened before that is like asking what the play was doing before the curtain rose. The stage didn't exist yet. There's something oddly comforting about that. The idea that time has a beginning gives the universe a sense of coherence, a boundary that defines everything that exists within it. Instead of imagining an infinite chain of befores receding into the past forever, we find a natural stopping point, not an end, but a limit, like the edge of a map marked with "Here be dragons." And yet, the possibility of timelessness is more than just an abstract notion. Some physicists suspect that even now time might not be fundamental. It could be an emergent property, like temperature or pressure, that arises only when you look at the collective behavior of countless particles. On the smallest scales, in the realm of quantum gravity, there might be no clock at all, just relationships, patterns, and probabilities. From that silent structure, time might emerge as an approximation, the way smooth water emerges from the chaotic dance of molecules. If that's true, then time as we experience it, with its rhythm, its flow, its arrow, might be a local illusion, a human-scale reflection of something deeper and more abstract. What we call the beginning of time could be the moment when the universe first became capable of experiencing change. Before that, the question "when" simply didn't apply. It's difficult, almost impossible, to imagine a world without time. Our thoughts, our language, even our sense of self depend on it. But perhaps that's the wrong way to think about it. The universe doesn't owe us intuitiveness. It began in ways our brains, evolved to find berries and avoid predators, were never meant to grasp. And yet, here we are, daring to ask questions that stretch beyond the limits of language itself. Maybe that's what makes the question beautiful. Not that we can answer it, but that we can understand why the answer might not exist in the way we expect. Before the Big Bang might not be a time but a boundary of understanding, the horizon where physics gives way to wonder. So if you ever find yourself staring up at the night sky and wondering what came before it all, remember the North Pole. There is no north of it. Not because there's something hiding beyond, but because north stops making sense there. The beginning of the universe may be just like that. Not a wall, not a curtain, not a secret. Just the quiet place where time at last runs out of words. At the smallest scales imaginable, the universe begins to stutter. The smooth fabric of space and time, which Einstein described so elegantly, starts to fray and shimmer, as if reality itself is made of something more fundamental. The forces that govern planets and galaxies work beautifully under general relativity. The rules that describe atoms and particles, the domain of quantum mechanics, are equally successful. But when you try to use both at once, they refuse to cooperate. It's like trying to play two perfect melodies together, only to find that, when combined, they make noise. Physicists have spent nearly a century trying to find the harmony between these two songs, to unite the small and the large into one grand theory of everything. That search is known as the quest for quantum gravity. The name sounds simple enough, but the task is monumental. It means finding a single framework that explains both the quantum world, where uncertainty reigns, and the gravitational world, where space-time curves and flows. It means describing the moment when the universe was so dense, so energetic, that quantum effects and gravity were one and the same, the very first instant of existence. At everyday scales, gravity is the calm, predictable force that keeps your feet on the ground and planets in orbit. Quantum mechanics, meanwhile, is anything but calm. It tells us that particles don't really have fixed positions or energies until they're measured, that they exist in overlapping probabilities, a haze of potential outcomes. The trouble is that Einstein's equations treat spacetime as a continuous, definite stage, while quantum physics says nothing is ever definite. Put them together and the math breaks. The equations give nonsense results. Infinities where there should be answers. So physicists have begun to wonder, maybe spacetime itself isn't fundamental. Maybe it's not the smooth, continuous stage we think it is, but a kind of illusion that only appears solid at large scales, like a digital image that looks seamless from afar but is really made of countless tiny pixels. In this view, space and time might emerge from something deeper, a web of quantum relationships, an invisible network of connections flickering in and out of existence. One of the most popular ideas in this field is loop quantum gravity. It suggests that space is woven from discrete loops, tiny indivisible quanta of area and volume. At the Planck scale, the smallest scale imaginable, space-time would look like a mesh of interlocking threads, constantly shifting and rearranging. There would be no points in space, no background grid, just a dynamic network, a cosmic fabric knitting and unknitting itself billions of times each instant. What we experience as smooth space and flowing time would be the large-scale average of that quantum dance. Much like how a flowing river seems continuous, even though it's made of countless water molecules. Another approach, string theory, takes a different view. Instead of treating particles as point-like objects, it imagines them as tiny vibrating strings, each mode of vibration producing a different kind of particle, an electron, a photon, a graviton. In this framework, gravity naturally emerges from one of the string's vibrational patterns. Space and time aren't fundamental here either. They are consequences of how strings interact. Some versions of string theory even suggest extra dimensions curled up so tightly that we'll never detect them directly, hidden within the ordinary 3 dimensions we move through. A more recent and intriguingly poetic idea is that the universe might be built from information. According to this perspective, space-time could arise from the entanglement of quantum states, the mysterious link that allows particles to share properties even when separated by great distances. Physicists have found that the geometry of certain spacetimes can be described by patterns of quantum entanglement. In other words, the connectedness of space may literally be the connectedness of quantum information. Reality then might be less like a fabric and more like a vast web of relationships, each node influencing the others through invisible ties of probability. It's a dizzying thought that time, space, and even the notion of distance might emerge from something that isn't spatial or temporal at all. In such a picture, the Big Bang might not have been an explosion in space, but the moment when space itself condensed out of a timeless quantum state, a kind of cosmic crystallization of possibility into geometry. Before that, there was no before, because time had yet to arise. Of course, these ideas remain speculative. None have yet provided the long-sought theory that can make precise predictions or be tested in the lab. The scales involved, the Planck scale, where gravity and quantum effects meet, are so minuscule that no experiment on Earth can probe them directly. But we can glimpse hints of quantum gravity in indirect ways. The ripples of gravitational waves, the radiation around black holes, or perhaps one day, the faint fingerprints left on the cosmic microwave background by the universe's earliest moments. The dream of uniting the large and the small has led to some of the most creative physics ever imagined. Some researchers propose that black holes, once thought to destroy information, actually store it on their surfaces, a clue that space-time might behave holographically, with three-dimensional reality emerging from a two-dimensional boundary. Others suggest that time itself could be quantized, made of discrete ticks so small that they blur into continuity. And still others imagine the universe as a kind of computation, where each interaction updates the state of reality according to quantum rules. If all of this sounds abstract, that's because it is. But there's a poetic resonance to it too. Each theory, in its own way, suggests that the universe is more than what it appears to be. That beneath the familiar flow of seconds and the vastness of galaxies lies something simpler, stranger, and perhaps more elegant. A pattern of relationships, probabilities, or vibrations that give rise to everything we perceive. Space and time might not be the stage, but the performance itself, the product of deeper harmonies we have yet to hear clearly. Even Einstein, toward the end of his life, dreamed of such unity, a single theory that could describe both the curvature of space-time and the jitter of quantum fields. He didn't live to see it, but his legacy inspired generations to keep searching. Today, that search continues, blending mathematics, philosophy, and imagination in equal measure. We don't yet know if the final answer will come from loops, strings, or something entirely new. It might even require rethinking what an answer means when the concepts of space and time themselves are up for revision. And perhaps that's the most profound part of all. Each attempt to understand the universe's quantum beginnings reminds us that our most basic intuitions, distance, duration, cause, may be emergent, not fundamental. The cosmos may not be a thing that exists in space and time, but something that creates them. What we call the beginning may not have been a moment, but a transformation, a shift from potential to actuality, from timelessness to history. For now, quantum gravity remains a dream, but a beautiful one, a glimpse into the idea that reality might be woven not from substance, but from information and interaction. Space could be a web of connections, time a rhythm that emerges from the dance, and the universe itself a poem still being written in the language of probability. We stand, as ever, on the threshold of understanding, staring into the quantum fog at the edge of the beginning. The equations may not yet sing in harmony, but in their dissonance you can almost hear the faint music of creation, the universe humming softly, still telling its first story. If the early universe could speak, what would it say? The first few moments after the Big Bang were so brief, so extreme, that they've long seemed beyond our reach. No telescope can see directly into that time. The light from those instants never escaped. And yet, the universe is not silent. Across its vast expanse, faint whispers from its earliest seconds still linger. We can't see the beginning, but we can listen for its echoes, the subtle ripples, patterns, and particles that remember what the universe was before it grew calm. These cosmic relics are scattered like fossils through the fabric of space. They're not found in stone, but in radiation, gravity, and even in the particles streaming silently through your body right now. Each one offers a clue to the universe's infancy, a kind of archaeology of the invisible. By studying these traces, gravitational waves, polarization patterns in ancient light, and the ghostly background of primordial neutrinos, scientists are slowly piecing together the first sentences of the universe's story. One of the most haunting of these relics is the possibility of primordial gravitational waves, ripples in space-time itself, launched during the universe's earliest instance. Unlike light, which scatters and fades, these waves could have passed through everything unimpeded, carrying with them a direct memory of the conditions at the very beginning. They would be the universe's original music, the vibrations of space-time as it first stretched into being. These waves would have been produced during inflation, that brief and astonishing period when space expanded exponentially. Tiny quantum fluctuations in the energy field driving inflation could have created gravitational waves, stretching and freezing them into the fabric of the cosmos. Billions of years later, they would still be passing through us, faint elusive distortions of space-time that ever so slightly stretch and squeeze everything in their path. Detecting them, however, is an extraordinary challenge. Gravitational waves are subtle even when produced by colliding black holes. The primordial ones are unimaginably faint. Instead of trying to catch the waves directly, scientists look for their fingerprints, patterns they might have left on the cosmic microwave background, the oldest light in the universe. That ancient light released when the universe was just 380,000 years old carries more than just temperature variations. It also carries polarization, a faint pattern in the direction of the light's electric field. If primordial gravitational waves passed through the plasma of the early universe, they would have imprinted a distinctive swirling signature, a pattern known as B-mode polarization. In 2014, astronomers working with a telescope at the South Pole announced that they might have detected those B-modes, possible evidence of inflation's gravitational waves. The scientific world erupted in excitement, but later it turned out that the signal was largely caused by dust in our own galaxy. The dream wasn't dead, just delayed. The instruments weren't wrong so much as the cosmos was subtle. The signature may still be there, buried beneath the noise, waiting for sharper eyes to find it. Since then, a fleet of experiments, on the ground, in balloons and in orbit, has continued the search. Satellites like Planck and experiments such as BICEP and SPT-Pol are mapping the polarization of the cosmic microwave background with ever finer precision. Each new observation brings us closer to hearing that faint gravitational hum from the beginning. If it's found, it will be one of the most profound discoveries in history. A message from the universe's first trillionth of a second. But even in the absence of a clear detection, silence itself speaks. The fact that we haven't yet found strong primordial gravitational waves tells us that inflation, if it happened, must have been gentler than some models predicted. The universe's quietness helps us narrow down its possible origins. In cosmology, absence is data too. Another whisper comes from particles far more elusive than light, neutrinos. They are the universe's most introverted citizens, nearly massless, electrically neutral, and capable of passing through light years of solid lead without slowing down. Trillions pass through you every second unnoticed. But among them lies an ancient subset, the cosmic neutrino background. These neutrinos were released just 1 second after the Big Bang, when the universe was still a hot soup of protons, neutrons, and electrons. They are older than the cosmic microwave background, older even than atoms. By now they've cooled to near absolute zero, making them practically impossible to detect. Yet their effects can still be inferred in the patterns of the cosmic microwave background and the distribution of galaxies. These neutrino fossils slightly influence how matter clumps together across space, a subtle fingerprint from the universe's childhood. Detecting the cosmic neutrino background directly would be like hearing the universe's very first breath. Several ambitious projects like the proposed Ptolemy experiment are being designed to try. If successful, they would allow us to study conditions that existed when the universe was only 1 second old, an astonishing level of cosmic archaeology. There's yet another possible relic, even more speculative, the faintest gravitational ripples that inflation might have generated across the entire cosmos. These waves would be incredibly long, spanning the size of the observable universe or more. They could subtly influence the large-scale structure of galaxies or the way the universe expands over time. Searching for them is like listening for a single, deep bass note that resonates across all of space. Almost inaudible, but omnipresent if you know how to listen. Every one of these searches, whether for waves, light, or neutrinos, is an attempt to connect with the universe's earliest moments, not by looking back in space, but by decoding the traces left behind in time. We may never see those first instants directly, but we can still hear their echoes reverberate through everything that came after. Even the tiniest patterns in the cosmic microwave background tell us something about the universe's youth. The fact that those patterns exist, the slight mottling of hot and cold regions, shows that the early universe wasn't perfectly smooth. Those ripples became galaxies, clusters, and cosmic webs. The faintest whispers of the early universe shaped the loudest symphonies of the later one. There's a quiet humility in the way cosmologists approach these mysteries. They build instruments on frozen plateaus, launch balloons into the stratosphere, and send satellites into deep space, all to measure temperature differences smaller than a millionth of a degree. They search for waves that might stretch space-time by less than the width of a proton. And yet, from these whispers, we've already learned that the universe is flat, to astonishing precision, that it's filled mostly with dark energy and dark matter, and that it began with a hot, dense expansion nearly 14 billion years ago. The faintness of the signal hasn't dulled our hearing. It has sharpened it. Sometimes, though, the silence itself is profound. There are signals we expected to find that remain missing, and each absence redraws the map of possibility. The early universe may have been quieter, smoother, or stranger than we imagined. In cosmology, silence is never empty, it's full of clues, and so we keep listening. Every improvement in technology brings us closer to the first heartbeat of the cosmos. The universe may never tell us everything about its beginning, but even its faintest murmurs are enough to guide us. Like archaeologists brushing away dust from an ancient artifact, we uncover more with each careful touch. Not full answers, but exquisite fragments. Perhaps that's how the universe prefers to speak. Not in shouts, but in echoes. Not in clear sentences, but in subtle vibrations carried across the ages. The earliest moments may be gone beyond recall, but their traces remain, woven into the background of space, carried by ghostly particles and written in the structure of galaxies. To listen to the universe is to practice patience. It hums on a timescale that dwarfs lifetimes, whispering truths that can take generations to hear. And even if the first sound of creation never reaches our detectors, we'll know something essential. that silence too is part of the story. The cosmos may never repeat its opening note, but it leaves us with its echo, faint yet eternal, still resonating through the quiet. The universe is vast beyond imagination, yet even that vastness has edges, not physical walls or borders, but boundaries set by time itself. These are the cosmic horizons, the limits of what any observer can ever see, no matter how powerful their telescope or how long they wait. They aren't there because something is hiding behind them, but because the universe is expanding faster than light can reach us. Beyond a certain distance, light from distant regions will simply never arrive. The cosmos stretches so swiftly that parts of it slip forever beyond our view. This idea can feel strange, even claustrophobic at first. We tend to picture the universe as a giant room that we might someday explore in full. But in reality, every observer, on Earth, on some distant exoplanet or in a galaxy far beyond our reach, sees a slightly different version of the universe. Each has their own observable horizon, a bubble of space defined by how far light has had time to travel since the beginning. Our observable universe has a radius of about 46 billion light-years, even though the universe itself is only about 13.8 billion years old. That's because space has been expanding all along, carrying galaxies away from one another like dots on an inflating balloon. If you could somehow stand at the edge of that cosmic horizon, you wouldn't find a wall, only more space, more galaxies, more of the same endless expansion. But light from those galaxies hasn't yet, and never will, reach us. Their story is written in a language that can't cross the swelling distance between us. In a sense, each observer lives at the center of their own cosmic sphere, their own island of knowable reality, surrounded by horizons that recede as the universe grows. The horizon isn't a fixed border, it changes with time. Long ago, our observable universe was much smaller. Fewer galaxies were visible, fewer lights twinkled in the cosmic darkness. As time has passed, light from more distant regions has reached us, enlarging the visible sphere. We are literally seeing more of the universe every moment, but paradoxically, also losing more of it to the accelerating expansion driven by dark energy. Galaxies that we can see today will, in the distant future, fade from view, their light stretched beyond detection. The universe will appear lonelier, though it won't truly be emptier. That interplay between what we can see and what we never will is a humbling reminder of perspective. From our small vantage point, we glimpse only a fraction of what exists. Even our grandest maps showing billions of galaxies chart only a tiny portion of the whole. Beyond our cosmic horizon may lie countless more galaxies, clusters, and perhaps even entirely different cosmic domains. The universe could be finite or infinite. We simply don't know. And we may never know. Every observer, wherever they may be, faces the same limit. Someone in a distant galaxy, billions of light years away, would look out and see their own horizon, also roughly 46 billion light years across, centered on them. Much of what we can see, they cannot. Much of what they can see, we cannot. The universe is, in that sense, democratic but deeply private. Each point in space holds its own observable sphere, its own view of cosmic history. There is no single, master perspective that contains it all. Even the cosmic microwave background, that faint ancient light we use as a kind of universal backdrop, looks slightly different from every location. The patterns of temperature and polarization shift depending on where you are and how you're moving. From one galaxy to another, the universe's story unfolds in subtly different ways. There is no single, absolute view, only many partial ones, overlapping like the reflections of stars in rippling water. This realization can be both humbling and oddly comforting. For centuries, humans have tried to see farther, to chart the whole of creation. Each new telescope, each new discovery, expands our horizon of understanding. But it also reminds us how much lies beyond. The edges of knowledge always move outward, but they never disappear. The more we know, the more we realize there is to learn. It's a beautiful irony. We live in an age when we can measure the universe's expansion, detect planets around distant stars, and glimpse the light of galaxies born when the cosmos was still young. Yet we must also accept that we will never see it all. There are parts of the universe whose light will never reach us, not because our instruments are weak, but because time and space themselves forbid it. Our maps will always be incomplete. But incompleteness is not failure, it's what makes discovery possible. In cosmology, horizons are not just limits to observation, they are reminders of our place in the grand story. They mark the divide between what is known and what is still unfolding, between what the universe has told us and what it still keeps to itself. They also invite humility. Science thrives not by pretending to have all the answers, but by learning to ask better questions, to listen more carefully to the faint signals that do reach us. And sometimes those signals surprise us. Every so often, a new observation pierces the horizon of our expectations. A faint gravitational wave arrives from a distant merger. A subtle polarization pattern reveals a new clue about inflation. A deep survey uncovers galaxies farther away and therefore older than we thought possible. Each discovery redraws the edges of our understanding, like a horizon shifting at dawn. It's worth remembering that our cosmic horizon is not a hard boundary in the human sense. It doesn't imprison us. It defines the scale of our curiosity. The very act of reaching toward what we cannot see, of asking what lies beyond the light, is part of what makes us explorers. We map the cosmos not to conquer it, but to understand where we stand within it. And in that search, we find something quietly profound. The limits themselves are beautiful. The fact that there is more than we can ever know means the universe will never run out of mystery. There will always be more questions, more hidden galaxies, more unanswered whys. The horizon ensures that wonder never ends. So while it's tempting to wish for a final map, a perfect picture of everything, that kind of completion might actually rob the cosmos of its allure. Mystery is not a gap in knowledge, it's a feature of reality. The universe seems built to keep a part of itself hidden, not as a trick, but as an invitation. The edge of what we know is not a wall, it's a window that keeps opening. Someday, long after our galaxy's stars have dimmed, future astronomers, if any remain, will look out and see far less than we do today. The cosmic horizon will have closed in around them, leaving only their local group of galaxies visible. To them, the wider universe will be gone beyond recall, but the light from distant galaxies will still exist, travelling endlessly into the unreachable. The cosmos even then will continue to whisper beyond the horizon. Perhaps that's the final lesson of the cosmic horizon, that not knowing everything is part of the beauty of the search. The universe's boundaries don't limit our curiosity, they give it shape. Every question we ask, every photon we catch, every theory we refine is an act of reaching across that endless distance. The horizon reminds us that knowledge has no final chapter, only new pages waiting to be turned. We will never see it all, And that's all right. The cosmos keeps its secrets with grace, offering us just enough light to wonder, to measure, and to dream. Beyond our horizon, the universe continues, infinite, mysterious, and serenely indifferent. Yet somehow, in that unreachability, it feels all the more alive. Time and space began together, not as separate threads, but as a single unfolding fabric. From that first expansion came light, matter, and the quiet laws that still guide the universe. Stars formed, burned, and died, scattering their elements into new worlds. Every atom in your body was once part of that ancient fire. You are, quite literally, made of the universe remembering itself. The flow of time that began back then hasn't stopped. It carries galaxies apart, stars through their lifetimes, and you through yours. Space gives form, time gives motion. Neither exists without the other. Together they create the rhythm of everything, from the spin of planets to the beating of a heart. We may never know what came before, if before even means anything. Maybe there was only stillness, no moments, no distance, just potential waiting to unfold. From that stillness came the spark of existence, and from that spark, everything we see and feel. The horizon of knowledge will always move just out of reach. There is no final map, no last discovery, only a deeper understanding that grows with each new question. And that's all right. The beauty of the universe lies not in certainty, but in wonder. As you close your eyes, remember, you are part of this same unfolding. The same expansion that carries galaxies through the void carries you too. The same silence that preceded the first light still echoes quietly within. You are made of time and space, the living continuation of the universe's first breath. And as you drift towards sleep, you're floating gently along the same cosmic current that began it all. Calm, endless, and still unfolding.